number vortex operators are typically Grassmann odd, and even ghost number vortex operators are Grassmann even. Now, this doesn't look like an infinite component field that I promised at the beginning. But to see these infinite components, what you need to do is to choose a basis in H and expand phi in that basis. And the idea is that the coefficients of expansion are the dynamical variables of the theory, which can be any number, and those are the fields. And that's where you get the infinite number of fields from. So given this description of string field, one can now write down an action, and the action for open and closed strings are very similar form. So the first term, these are the kinetic terms and these are the interaction terms, which in general is non-polynomial. Q is a BRST operator in the matter ghost conformal field theory. This curly bracket operation, as it suggests, is a multilinear function of the fields. So given A1 to n in the vector space H, this curly bracket is an n-point correlation function of the vortex operators A1 to n on the disk or sphere, depending on how they are doing open or closed strings. But this correlation function is then integrated over some specific codimension 0 subspace of the moduli space of disk or sphere with n punctures. So it's not just correlation function at a particular point in the moduli space, it's a correlation function integrated over some subregion of the moduli space. Also, since the vortex operators are in general off shell, we are not imposing any on shell condition on the string field. They have to be inserted on the disk or the sphere with some specified local coordinates around the punctures. Because if you change the local coordinate system, typically these correlation functions will change. And this choice of what codimension 0 subspace you integrate this over and what local coordinate system you choose to define the correlation function, these are correlated. Okay? These are not completely independent objects. Now, with appropriate definition, one can show that this product, this n string product, this is a number constructed out of n string fields. This has cyclic symmetry for open strings and full permutation symmetry for closed strings. Given this, which I defined earlier, we also defined a square bracket. This time it's not a number, it's an element of the Hilbert space H. And this is defined by describing its inner product with an arbitrary state in H. So for open strings, we define the inner product of an arbitrary state in H with this square bracket as simply the curly bracket of C and A1 to n. And for closed strings, there is a similar definition, except that in this inner product, you insert a C0 minus. And this is necessary because the states in H are annotated by B0 minus. So this, once we have defined these curly brackets as integrals over some subregion of the moduli space, these are completely defined by these two formulae over here. So what one can show that the string field theory action that we construct this way is invariant under infinitesimal gauge transformation, and the gauge transformation for open strings and closed strings take this form. Here lambda is the infinitesimal gauge transformation parameter, which itself is a state in H with ghost number 0 for open strings and the ghost number 1 for closed strings. And again, by decomposing lambda in a particular basis of H, we see that there are infinite number of parameters hidden inside lambda. So not only we have infinite number of fields, but we also have infinite number of gauge transformation parameters in this theory. And one can show that the action is invariant under these transformations. And the linearized transformation, where we ignore these interaction terms, is simply a statement of BRST invariance. This tells us that adding a pure BRST state is like having a gauge transformation. Now, because you have this infinite parameter gauge invariance, you have to gauge fix, and that requires introducing ghosts. And it turns out that when you introduce ghosts by gauge fixing, the set of all ghost fields for plus matter fields correspond to a state in H with arbitrary ghost number. Now, this is somewhat surprising, but this is a particular property of string field theory, because the ghost fields that we are referring here are the ghost fields that come from gauge fixing the string field theory, where the ghost number that is being referred to here is a ghost number in the worldsheet theory. Nevertheless, one finds that upon gauge fixing, all we need to do to introduce the set of all the ghost fields is to relax the constraint on ghost number and the states in H. So the action with matter plus ghost has exactly the same form as in the original action, except that there is no constraint on the ghost number of phi, because phi now represents both matter fields and ghost fields. And there is a natural framework for quantizing this, which is called the Batalin-Vilkovsky or BV formalism. So after gauge fixing, we can compute Feynman diagrams, and what one finds is that each tree Feynman diagram gives integration over part of the moduli space of punctured disk or punctured sphere, depending on whether it's open or closed strings, and when you sum over all Feynman diagrams, then you get back integration over the full moduli space. Okay, again, this is a result that goes back to the early days of string field theory. What about loops? Generically, open string field theory at the loop level requires coupling to closed string field theory, because as we know, open string field theory loops actually generate closed strings. Closed string field theory, on the other hand, can make sense by itself. So what one finds is that when we try to include loop effects, the action has similar form, except that in the definition of this curly bracket, we now have to also add new contribution that involves integration over the subspaces of moduli space of higher genus surfaces. Now, it may look surprising that you are changing the action as you go to the loop level. Normally, the action is fixed and you only compute Feynman diagrams. But we can understand these additional terms that we need at the loop level as finite local counter terms that are needed for maintaining gauge invariance. Okay, so these are not infinite counter terms, but these are finite local counter terms that you have to add, because the integration method is not gauge invariant. And the same counter terms also ensures that the sum over all Feynman diagrams at the loop level gives correct result for on-cell amplitudes, okay, by integrating over the full moduli space of Riemann surfaces. So there is, however, one exception to these general rules that I described, and this is the cubic open string field theory of Witten. This uses spatial choice of local coordinates for defining this 3-point vortex A1, A2, A3. And it turns out that once you use this particular choice of local coordinates for defining this 3 vortex, then we do not need any other vortex, neither at the tree level or at the loop level. Okay, just cubic vortex is good enough. And there is also no need to couple to closed strings, at least for on-cell amplitudes. Okay, for on-cell open string amplitudes, you can get by without adding closed strings. So for this theory, one uses a spatial notation. Okay, this square bracket that I introduced earlier. Now, of course, there is no hard square bracket because there is no hard point coupling. The square bracket is often denoted as A star B, as a star product, or just AB sometimes. Now, it should probably be clear from the description that the string field theories that we have constructed this way are not unique. They are not unique because we have different possible choice of local coordinate system at the punctures, and these lead to different string field theories. Now, this seems like a bad news. There is a proliferation of string field theories. Fortunately, one can show that all these different field theories that you get by different choice of local coordinates are related by field definition. So effectively, you are describing the same system, but in different field, using different field coordinates. Nevertheless, some choice may be simpler than the others. Okay, and the prime example that I described in the last slide is the cubic open string field theory. This corresponds to one particular choice of field definition that makes the action purely cubic. Unfortunately, there is no analogous simple choice for closed string field theory. So there is a particular proposal that was made by Zoibach, which uses minimal area metric, okay, which uses the local coordinate system that is induced by what is called a minimal area metric. And the idea is that it minimizes the area of the Riemann surface subject to a lower bound on the length of all non-trivial closed geodesics. So this defines a metric, and using that metric you can introduce a set of local coordinate systems around the punctures. And the proposal of Zoibach was that you can use that as one particular definition of closed string field theory. Unfortunately, it's hard to construct such metrics, and very few explicit examples are known. So this is old story. So now let me just say in one slide what are the new developments on this front. So there have been some new developments on this front. Okay. First, this is a talk that we'll hear next. Musavian and Pius, they proposed a choice of local coordinates based on constant negative curvature metric on the Riemann surface. Okay, so this is distinct from the minimal area metric that I described in the last slide. So this metric needs to be modified near the boundaries of the moduli space, but they have a systematic procedure for constructing this metric. And so in principle, this gives you one particular definition of closed string field theory, okay, where the local coordinate system can be constructed explicitly. The other progress is that recently Heydrich and Zoibach developed a systematic tool for numerically constructing the minimal area metric. So both approaches are useful for providing explicit definition of off-cell string amplitudes, because they correspond to providing a particular coordinate system for defining for string fields in terms of which you write down the action. So now let me turn to superstring field theory. And I'll be using the RNS formulation and describe what we know about superstring field theory in this formulation. Now, in RNS formulation, there are two equivalent approaches to perturbation theory. One is based on integration over supermoduli space. This is more geometric. The other one is based on using picture changing operators. Okay, so these are some particular local operators that one uses for purpose that I'll be describing soon. So far, mostly the second approach has been used in the construction of string field theory, so I'll be focusing on this approach, picture changing operators. So in RNS formulation of superstring field theory, the Hilbert space becomes a direct sum of Hilbert spaces of different picture numbers. So this is a particular quantum number that arises in the RNS formulation, and you can write the Hilbert space as a direct sum of all these Hilbert spaces. This n can be integer that describes an NS sector, or it can be half integer that describes a Ramond sector. And one can show that on cell all n are equivalent, all integer n are equivalent, and all half integer n are equivalent. The canonical choice for open string field that one normally takes is that NS sector fields have picture number -1 and the Ramond sector fields have picture number -half. And for closed string field, this just gets doubled. Okay, so this is, for example, the NS-NS sector, this is the RNS sector, NSR, and RR. Now, going back to the worldsheet description of string scattering amplitude, if we are going to compute a G-loop amplitude of m NS and n Ramond sector states, what we need to do is to insert 2G minus 2 plus m plus n by 2 picture changing operators for picture number conservation. Essentially, because on a genus G Riemann surface, we need a total picture number 2G minus 2 to get a non-trivial correlation function. Yeah, and we have to compensate for the picture numbers of the vertex operators, and that's what leads to this number. Now, it turns out that the result for the on-cell amplitude is independent of the locations of the picture changing operators. It doesn't matter where you insert the picture changing operators, provided we choose them avoiding spurious singularities. Now, spurious singularities is a long subject, but let me just say that it's any singularity that depends on PCO locations is called spurious singularity. And the simple examples are these are just when two PCOs collide or a PCO collides with a vertex operator. Okay, but there are more complicated examples of spurious singularities. And the idea is that as long as you choose the PCO locations avoiding these spurious singularities, you can show that the result is independent of where you choose the PCO locations on cell S matrix elements. And it turns out that there is also a systematic procedure for avoiding collision of PCOs or avoiding any spurious singularities. So you have a completely well-defined string perturbation theory based on PCO insertions. However, when you try to define off-shell amplitudes, they depend on PCO locations, just as they depend on the local coordinates at the punctures. Okay, because off-shell vertex operators are of course not conformally invariant, nor are the BRST invariant. Now, for NS sector fields, or NSNS for closed strings, the tree-level string field theory can be constructed following the same procedure as in bosonic string field theory. Okay, this in fact also goes back to early days, okay, although there are some recent developments that I'll be describing later. So the PCO locations enter in the definition of this curly bracket, because now we also have to insert PCOs to make sense of this. But again, one can show that different string field theories associated with different choice of local coordinates and PCO insertions are all related by field definition. So even though apparently the string field theory depends on what local coordinate system you choose to define the off-shell amplitude and what PCO insertions you use, the final result is independent. The physical results are independent of those choices because it's just field definition. The Raman sector turns out to have additional complications. And the additional complication arises from the fact that two phi's, if you take phi to have picture number minus half, which is the canonical choice, two phi's have total picture number minus 1, but we need picture number minus 2 on a genus 0 Riemann surface to get a non-vanishing correlator. So you are missing a picture number minus 1. Okay, we need additional picture number minus 1 at genus 0. So we cannot simply write down a kinetic operator like phi q phi because that doesn't have the right picture number. Now this looks like a technical problem, but one can show that in fact this problem goes much deeper because this is related to the absence of a covariant kinetic term for type 2b supergravity due to the self-dual five-form field strength. Okay, so that the absence of an action for type 2b supergravity or type 2 string field theory is essentially tied down to this strange feature of picture number conservation. Now it turns out that there is a resolution to this problem, and the way you can resolve this problem is that in the Raman sector we can introduce another string field which I'll call psi, which now has picture number minus 3/2, and then we write the kinetic term in this form. Okay, so here you can see we inserted this operator G, which is a 0 mode of the picture number of picture changing operator. So here you have minus 3 total picture number from here, and last one from G, so you have minus 2. Okay. And here psi has picture number minus 3/2, phi has picture number minus 1/2. So again you have picture number minus 2. So this action makes sense. The interaction terms involve only the original fields phi. And when one goes to the analysis of this field theory in some detail, one finds that one combination of psi and phi remains free field all through and decouples from the theory, and then the rest of the degrees of freedom describe correctly the interacting string field theory. So the idea is that you can solve the problem in the Raman sector by adding an extra free field in the theory. So this construction also works at the loop level exactly as in the case of bosonic string theory. And again the string field theory action depends on the choice of local coordinates at the punctures and the choice of PCO locations, but all such theories are related to each other by field definition. So now we turn to the question about whether there is a simple choice that is simpler than the others. Okay, just like Witten's string field theory, cubic string field theory. Now it should be clear that this is difficult for closed string theory because even the bosonic closed string field theory does not have a simple choice. Okay, so you can't really expect that closed superstring field theory will have a simple choice of these vortices. However, there has been progress for tree-level open superstring field theory, and this is what I'll be describing next, okay, which involves making simple choices of the picture changing operators and the local coordinate system. So again the history of this goes back to 1990s, So in 95, Berkowitz constructed a tree-level open superstring field theory with string field phi in what he called the large Hilbert space. So what is a large Hilbert space? A large Hilbert space contains states of arbitrary integer picture number. So this of course has many more fields, but this also has extra gauge invariance. And this reduces the number of degrees of freedom, and the action can be written in a compact form. It's gauge invariance. It's hard to show that the sum of Feynman diagrams give the correct amplitude, even for the 4-point function, but we expect this to be true, and we have more to say about this later in this talk. But the general experience is that if we have constructed a string field theory with the correct cubic interaction, and if it has the full gauge invariance, then most likely it's the correct string field theory, that it will reproduce the amplitudes correctly. In 2013, Euler, Komatsu, and Sachs, they constructed an open superstring field theory for NS sector fields, which generalizes an earlier construction of Witten. So Witten, again in the 80s, had constructed a version of open superstring field theory, but it was somewhat singular because the 4-point function, when you computed the 4-point function, the PCOs collided, leading to some singularities. So they resolved this problem. So first of all, they chose local coordinates at the punctures that are similar to those used in cubic open bosonic string field theory. And the PCO insertions were smeared, that instead of having PCO insertion at one given point, they use integrals of the picture changing operators, which alleviate the singularities that arise from PCO collisions. Their action was not purely cubic. They needed to add higher order vortices, but there are simple algorithms to generate them maintaining gauge invariance. And this one could show that reproduces correctly the 3 amplitudes of NS sector states, all 3 amplitudes. So this can be called a simple version of open superstring field theory. Recently, Berkowitz open superstring field theory was shown to reduce to this formulation based on PCO insertions after partial gauge fixing. And since the second formulation is known to reproduce the amplitudes correctly, this also gives an indirect proof that Berkowitz open superstring field theory, in which the amplitudes are hard to compute directly, also reproduces all the tree-level NS sector amplitudes of open superstring theory. What about the Ramon sector? So what one finds is a doubling trick that I described earlier can be used to get a simple version of open superstring field theory, including the Ramon sector fields. This again uses local coordinate systems that are similar to the one for cubic open bosonic string field theory. And there is a fully systematic construction of smeared PCO insertions. Now there is a different formulation of open superstring field theory, which was given by Kunitomo and Okawa. So what they did is that instead of taking the string field phi to be an arbitrary element of H minus half, namely instead of allowing the string off-shell string field to be an arbitrary vertex operator of picture number minus half, they put additional restrictions on phi. These are analogs of the L0 minus phi equal to 0 constraint for closed strings, but they are more complicated. Okay, this is of course all being done at the level of the open strings. So they constructed an action which is quadratic in the Ramon sector fields, but have higher powers of NS sector fields. So in this action, checking that Feynman diagrams reproduce the amplitude is hard. This has been tested up to some tree-level 5-point functions. But as I said, the very fact that it's gauge invariant, they have proved gauge invariance to all orders at tree level. The very fact that it's gauge invariant and that it has correct cubic vertex is a strong indication that this will reproduce the string amplitudes correctly for all tree-level amplitudes. Finally, I should say that recently a new approach to classical open string field theory has been developed by Omori and Okawa. This is based on integration over the supermoduli space. But I think it's fair to say that it's still in its infancy. The action has not been constructed fully, but you should stay tuned, and maybe by the next string conference there will be more news on this. With this, now I turn to the second topic, and that's classical solution in open string field theory. So this, as I said, is one of the applications where string field theory has been somewhat successful. So the classical solutions are constructed by two different methods. One is numerical, or what is also sometimes called the level truncation, and the other one is analytical. And there are various people involved in this, and of course also here, and I'll mention some of the names as I go along. So let's first discuss numerical solution on D-branes. So what does it involve? So what we do here is we expand the string field in a basis of L0 eigenstates. Okay, the string field, as I have said, is an element of the vector space H. So you can expand it in a basis of L0 eigenstates like this. And then we, by brute force, we truncate the expansion to those phi n's for which L0 eigenvalue lie below some fixed number L. And we also impose some further symmetry restrictions. For example, if you are looking for translation invariant solution, we only allow zero momentum basis states over here. Then with this truncated string field, we just evaluate the action, and then we extremize with respect to the parameters n to find a solution. Okay? This is like extremizing the action with respect to the fields, except that you don't extremize with respect to all fields, we only extremize with respect to a subset of the fields. And the hope is that as we increase L, the solution converges to something nice. It turns out that this has been successful in generating many solutions in Witten's cubic bosonic open string field theory and also Berkowitz's open superstring field theory. Okay. The newer versions of open string field theory has not been tried so far, but that's because they are new. Okay. Maybe someday somebody will try finding solutions in those theories as well. So here are some examples of what kind of solutions one can find. A tachyon vacuum describing the vacuum without D-brane. So you start with a D-brane, you switch on some fields, and then you find that there is a particular solution that describes the vacuum where the D-brane has disappeared. There are also soliton solutions that one can find which describe lower dimensional D-branes. So you start with a dp brane, and we find solutions which describe a dp minus 1 brane. And we can compute the energies carried by the solutions, and they come quite close to the expected energies of the D-brane configurations that they attempt to describe. Okay, that's the way you recognize that we have got the correct solutions. But given this, we can ask, can we use this approach to construct new solutions that are not known otherwise? So these will correspond to some new boundary conformal field theories. In open string field theory, it corresponds to some new boundary conformal field theories. And indeed, recently some solutions have been found which have no obvious description as D-branes. This is still an unpublished work by these authors, Martin Schnabel and two of his students, Mathieu and Jakub. So I'll try to describe the result in a few words. So the setup here is a D2 brane of bosonic string theory, which is wrapped on a two-dimensional torus. It turns out that there exists numerical solution in level truncation which do not have obvious CFT interpretation except at spatial points in the moduli space of T2. At spatial point in the moduli space of T2, which is given here, one can construct boundary state analytically with the help of enhanced chiral algebra. Okay, so at this point there is an enhanced chiral algebra, and one can impose new boundary conditions which are not the standard D-brane boundary conditions of imposing Neumann or Dirichlet boundary condition on the coordinates. And when they looked at this analytic solution at the spatial point and compared with their solution, they find that the energy density profile agrees between the numerical and analytical results. But of course, they can find their solution away from the spatial point, where there is no obvious interpretation of what these boundary conformal field theories are doing. So here is a picture taken from one of the talks. So here there is a comparison. So on this left hand side diagram is a plot of the numerical result for the energy density profile for this solution. This is a D2 brain T2, and on the right hand side is the analytical results for the energy density profile, and you can see that they match reasonably well. So this in a sense demonstrates the utility of open string field theory in looking for new conformal invariant boundary conditions. So with this, let me turn to analytical solutions in cubic open string field theory. So the first solution is due to Schnabel, which again goes back to 2005. This describes the tachyon vacuum on the DP plane. Okay, so this, the same vacuum that people are studying earlier with level truncation, it was found by Martin analytically. And he also showed that the energy density of the vacuum is the minus the tension of the DP brane. So essentially, if you add it to the original tension of the DP brane, you get 0 for the energy density of the vacuum, which is of course what we expect if the solution describes a configuration without a D brane. So this solution unfortunately is given in a different gauge. It's called the Schnabel gauge and not in the Siegel gauge where the level truncation analysis is carried out. So one cannot directly compare his solution, the Schnabel gauge solution for tachyon vacuum, with the earlier results of level truncation that we got in the Siegel gauge. Okay, nevertheless, it's believed that the two solutions are really gauge equivalent, okay, because they have the same energy density. So there have been subsequent developments which have provided better understanding of the solution and also paved the way to finding more analytic solutions. Yeah, in fact, this started with the work of Yuji Okawa, who reformulated Schnabel solution in a nicer form, okay, which is called the KBC algebra that I'll be describing in the next slide. Okay. And based on that algebra, one could construct many different analytic solutions. In a somewhat related work, Rastilian and Zoiberg computed the Venezian amplitude in the Schnabel gauge and got the same result. Yeah, and this confirms that the Schnabel gauge actually is a valid gauge choice. So it's not a singular gauge choice, because otherwise one would worry about whether a solution found in Schnabel gauge is a valid classical solution or not. Okay, so everything seems to be consistent with the Schnabel gauge. So later, based on this work of Yuji that started with the work of Okawa, Euler and Schnabel wrote down what they called a simple solution, a simple version of the Schnabel solution, okay, which is given here. Now this of course looks nice, but I have to explain what these various symbols are. So K, B and C are in some sense string fields, particular string fields that are constructed from line integral of the stress tensor, that is K, some line integral of the B ghost, that's B, and some insertion of the C ghost, that's C. So each of these are string fields, and all products that you see here are star products. And of course, when I say line integral of the stress tensor, you have to specify what coordinate system you are using, because stress tensor is a dimension 2 field and its line integral is not conformal invariant. Okay, so you have to specify what coordinate system you use to do this line integral, and that's part of the definition of what K, B and C mean. The purpose of showing this is to demonstrate that indeed it is possible to write down nice analytic form of the tachyon vacuum solution that Martin found earlier. And the other point that this analysis revealed is that in some sense the solution for the tachyon vacuum is at the verge of being pure gauge. In fact, there is a one parameter family of solutions where you put some constant lambda over here, which lies between 0 and 1, and put some multiplicative factors outside. And one can show that solution is pure gauge for any lambda less than 1, and at lambda equal to 1, it ceases to be pure gauge and it becomes a tachyon vacuum solution. So in some sense, the tachyon vacuum is at the verge of being a pure gauge. It's not clear whether this has any deeper significance. Now, people then went ahead and looked for other analytic solutions. So let's suppose that the world sheet theory has a boundary marginal deformation by some operator phi, then we should have a family of boundary conformal field theories, because a marginal deformation produces a family of boundary conformal field theories. All of these provide consistent background for open string theory, and hence there must be a family of solutions in open string field theory that describe the family of consistent background. And the question that one might ask is it possible to construct such solutions analytically? This was answered by these authors, and the answer turned out to be yes, provided the operator product of V and V has no singularity. Now this is a tall order, because standard time independent operators will have a z minus w to the minus 2 singularity. If you have two marginal operators, two operators of dimension 1, and take their operator product expansion, you will get a term proportional to the identity operator in the leading expansion. So one might wonder, how can you have no singularity in the VVOP? One way will be to construct time dependent operators where the operator carries a factor like e to the ax naught, and then the product of two such operators can be made to avoid any singularity of this form. But there is a more general remedy, okay, if you want to use time independent operators, which is that we can add a term proportional to I del x naught is the time coordinate, to the original vertex operator. Instead of using V, you use V plus some constant terms I del x naught, and you just simply adjust that constant so that there is no pole in the OPE. Okay, because VVOPU will have a singularity, but the OPE of del x naught itself will have a singularity with a negative sign, and they will simply cancel. And this is harmless because this just corresponds to switching on a constant A0, okay, which is pure gauge anyway. So this way people constructed analytic solutions describing marginal deformations, and there have been many subsequent developments simplifying the construction, and this paved the route for further developments. Now before I describe these further developments, let me just address one issue, which is that given a new solution, how do you know what it represents? Okay, suppose somebody gave you a solution in open string field theory, and you want to know what is the physical significance of this solution. And the answer to this, which was provided by Elwood, is that we simply try to explore how a closed string fills the solution. So the Elwood invariant essentially is a two-point function that involves a closed string and open string field, a two-point function of a closed string, vertex operator, and an open string field that describes the classical solution. And this invariant tells us how a closed string senses the particular solution. For example, what is its tension? Does it carry Ramon charge, etc. Okay, because all those can be sensed by closed string background. And this was later used to give an algorithm for constructing a boundary state associated with a given solution for open string field theory. Okay, so given a solution to open string field theory, these authors give an algorithm that generates a boundary state that describes the corresponding boundary conformal field theory. So given this, we can be more ambitious and ask, can we construct analytic solutions associated with non-marginal deformations? For example, take a D1 brane wrapped on a circle of radius r. Can we find an analytic solution that describes a D0 brane? This is possible in level truncation, but now we are asking whether it's possible analytically. This was answered in the affirmative by Euler and McAfee. So they gave a way to construct a solution of this kind, and they made use of what are called boundary condition changing operators, which are vertex operators inserted at the boundary, with the property that on one side you have one boundary condition, say a D1 brane boundary condition here, and on the other side you have the another boundary condition, say in this example D0 brane boundary condition here. And by making use of these boundary condition changing operators, they could construct explicit classical solutions that describe a string field theory construct. So they took the string field theory construct and using boundary conformal field theories with boundary condition BC1, and constructed a solution that describes string boundary CFT with BC2 with a new boundary condition. Okay, so this is like starting with a D1 brane and finding a solution that describes a D0 brane. So furthermore, their solution took a very suggestive form. Here, this is a tachyon vacuum solution. And psi star in some sense is the tachyon vacuum solution in the second string field theory around BC2, but this of course has to be written in the variables of string field theory around BC1, okay, because the whole solution is in the string field theory around BC1. So physically you can interpret this as the solution. What it is doing is that it's first creating the tachyon vacuum, that's what psi TV represents, and then subtracting from this the tachyon vacuum solution of the second string field theory, okay, to get the brane that you want. Okay, so you start with the D1 brane, go to the tachyon vacuum, okay, and then you subtract of the tachyon vacuum solution for the D0 brane to create the D0 brane. Finally, one can ask, what about classical solutions in superstring field theory? There have been some heroic effort by Ted earlier, but I should say that it's still in its infancy. Okay, so I'll not say much more about classical solutions in superstring field theory. Now, before I leave this subject of classical solutions, let me just mention an open problem, okay, which has been around for quite a while. And the problem is that suppose we find a string field configuration that satisfies equations of motion. How do we know if the solution is singular or non-singular? What is the criteria? The problem is complicated because there is no natural norm in the space of string fields. And so we cannot simply say that you just demand normalizability of the field phi, of the state phi, and only normalizable states will be allowed, okay, because there is no natural norm in the space of string fields. And indeed, there are currently many solutions, including some strange ones that seem to have negative tension, and the interpretation of this is unclear because of this issue. We don't know whether these solutions are physical or not physical. So far, the experience shows that all solutions that are found in single gauge level truncation, solutions which converge in the level truncation analysis, are sensible, but this is perhaps too restrictive. So now we turn to the next topic, okay, which will be very brief, the background independence. So what do you mean by background independence? Okay, now we are back to closed string field theory and also open string field theory together. Okay, we are not talking about exact classical solutions anymore. Now, we know that construction of string field theory requires choosing a particular classical background. Okay, this is encoded in the fact that we have to start with some conformal field theory that describes the worldsheet theory, and then the action is given in terms of the correlation functions and the BRST operator in this worldsheet theory. If you remember the form of the action, the first term had the phi q phi, that q refers to the BRST operator of some particular conformal field theory, and the curly bracket that I defined involves calculating correlation function again in some particular conformal field theory. So certainly the string field theory action depends on what conformal field theory you started with. And so now the question that one might ask is that how are string field theories constructed using different CFTs related to each other? Now, it turns out that when the two CFTs are related by marginal deformation, the answer is relatively simple. And the answer that one finds is that the true string field theories are related by field redefinition. So for bosonic string field theory, the explicit field redefinition was constructed in the 90s. And so basically the field redefinition was constructed for infinitesimal marginal deformation. And then the idea is that once you know how the field redefinition works for infinitesimal deformation, we can then integrate it to get the result for finite deformation. So this construction has also now been generalized to superstring field theories, including the Ramond sector. One subtle point that one finds is that only the interacting part is background independent. Okay, as I described, that in order to incorporate the Ramond sector, we have to introduce an additional field which becomes a free field at the end. It turns out that the free field part actually is background dependent. Okay, but we don't really care because that's not part of string theory. That decouples from the rest of the system anyway. Okay. The part that involves the scattering of string theory, okay, that part is background independent. So for open string field theory, one can in fact do it slightly better, because using this boundary condition changing operator, one can actually construct explicit field definitions that relate string field theories formulated around finitely separated backgrounds. Okay, so you don't have to go through infinitesimal deformation, and also you don't have to necessarily restrict yourself to marginal deformation. So this is my final slide before conclusion. Okay, this is a one-page summary of application to perturbation theory, because as I said, that's one of the motivations for studying string field theory. But here I'll be very brief, just describing the results. So the idea is that using the description of amplitudes as sum over Feynman diagrams, one can use techniques of quantum field theory to prove general properties of these amplitudes, okay, which are not always visible in the context of worldsheet description, okay, which gives only one term at every loop order. So first one can prove unitarity of perturbative S matrix using this. Then one can provide a systematic procedure for computing finite mass denomination of massive particles, which, as I again described, is not possible in the standard worldsheet formulation. And one can also develop a systematic procedure for computing string amplitudes when the perturbative vacuum gets destabilized and settles down to a nearby stable vacuum. Again, this is not possible in worldsheet description, because in the worldsheet description, you always start with a particular conformal field theory. And if it so happens that the quantum corrections destabilize that conformal field theory, you don't have a formalism by which you can readjust your background and try to look for nearby solutions. These are not classical solutions, these are quantum corrected solutions. But that procedure doesn't exist within conventional worldsheet description. So this is a summary of the talk. So first I should say that we now have a complete formulation of field theories of all string theories, although the formulation of closed string field theories remain complicated, okay, because of the fact that there is no simple version of closed string field theory. The most ambitious goal of string field theory would be to give a non-perturbative definition of string theory using path integral and string field action, but this certainly has not been realized so far. Nevertheless, on two fronts, it has had reasonable success. The first one is classical solutions in open string field theory. And as we saw, both numerically as well as analytically, we have made a lot of progress. And the second aspect that I described is that string field theory provides a systematic procedure for string perturbation theory in case of finite mass denormalization or when the vacuum gets shifted by quantum corrections. So, thank you.
Thanks for a very informative review. Questions?
Well, thank you for this very nice overview. When you talk about the superstring, the full superstring, including Neveu-Schwarz and Ramond sectors, I presume your gauge transformations also contain local supersymmetry transformations?
Yes, indeed.
And then the question is, does this really correspond to an off-shell realization of supersymmetry?
No, most likely not, because the commutator closes up to equations of motion. So it's not an off-shell realization. It's off-shell, but it doesn't close off-shell. The supersymmetry algebra doesn't close off-shell.
So something you said in the beginning of your talk, which is I found a little puzzling. So you said that the worldsheet approach, of course, gives one answer for a calculation, yes, but that may not be the best thing because sometimes we want to look at the propagator correction. But, yes, but the propagator correction is anyway not part of worldsheet string theory because it's on-shell, it just gives the S matrix element, right?
Yeah,
so that has amputated legs.
No, they are not amputated. Okay, let me go back to the diagram. Yeah. So what the worldsheet theory does is to amputate just this leg, not this whole thing. But you can see that if you amputate this leg and put things on shell, right, you get the poles, right? You are sitting right on the poles, and you get divergences. And these divergences show up when you actually do the worldsheet calculation. Okay?
So this is for the same reason that worldsheet theory is on shell only at tree level. That's
exactly
of the point.
That's right. So you have to renormalize.
I see.
Right, and that procedure doesn't exist within the worldsheet description.
Yeah, thanks.
Yeah, I had two questions. One is that in the RNS formulation of superstring theory, you have an infinite number of interactions involving regions in moduli space.
Yes.
Do you expect to meet the problems with the fact that supermoduli space is not split?
Yeah, I don't think that problem will show up here because we are not demanding that we have holomorphic choice of the PCOs. If you demand that the PCO varies holomorphically as a function of the moduli, then you run into that problem. But the way we solve this problem here is that we cut up the moduli space in many regions. In each region, we choose some PCO locations which avoid spurious singularities, and then you have a correction at the boundary, okay, where the PCO location jumps from one configuration to another configuration because neighboring regions need not have the same PCO insertions, and that correction is well defined. Okay, and you don't encounter any problem with the
even at higher genus,
Yeah, even in higher genus, because this is
Donagi and Witten, I thought, found non-splitness in families, deep inside supermoduli space.
Yeah, but I think that relates to, in the PCO language, that will translate to wanting to have a holomorphic choice of the
I see.
PCO.
So it is split
maybe,
in the C infinity category. Okay.
I think
so,
maybe Edward can comment.
Okay. So it's you're giving up holomorphy, and so okay.
Yeah.
So the other question is about the background independence. If I consider a family of CFT stages with a flat torus, flat metric, flat B field,
okay.
Are you saying that there should be does that imply that there should be a flat T-duality invariant connection on the space of conformal field theories over that Noreen moduli space?
Not necessarily. I have not thought about it. This is only infinitesimal, right?
No, but you said you could integrate it.
Well, you can integrate it, but it need not be that if you integrate it two different ways, you have
that's
the same
exactly my question. Is it flat? I mean, you better not have to choose a path.
Well, you may choose a path, and if suppose two paths gives two different Philly definition, right? That will just say that you are ending up with two different with gauge equivalent configuration with string field theory, right? So given a string field theory, you can make a gauge transformation.
I see. Okay.
If you start with open string field theory with one D brane, has the solution to two D branes in the same place been found?
Well, see, there are solutions of that kind. But whether the solutions are physical or not is this question of what corresponds to non-singular solution.
The solutions and try to see the non-abelian gauge symmetry, for instance.
No, I don't think that has certainly not has been done. That has not been.
Okay, I'll ask the last question. So you have a treatment of perturbative corrections that change the potential and shift the vacuum and then going around a new vacuum. Could you develop the same thing for a non-perturbative correction, say instantons and D-branes in open string theory?
I think if you have open string field theory on a D-brane, you can construct instanton solutions in principle. Right. Because they are, if you go to the Euclidean space, then you should be able to construct instanton.
And then to be able to, if they correct the potential, to then
incorporate them in a path integral. Yeah, see that suffers from the problem that you have to include closed strings typically, right? You have to, when you talk about path integrals, you have to, before you add the instantons, you have to also talk about the loops, right? And that generates the closed strings automatically, right? So you have to solve that problem before we talk about including instanton corrections. But if you did have a good path integral description of the open string field theory, non-perturbatively, then you could include instantons.
Okay.
Because the solutions exist.
Right. Okay, thanks. Well, let's thank Ashok-san again. next speaker is Roji Pius. What do you speak about? Hyperbolic geometry and quantum closed superstrings.
I would like to thank the organizers for the invitation. Today I will be talking about quantum closed superstrings and hyperbolic geometry. So we know that the scattering amplitudes in string theory are defined as sum over all possible string diagrams, and string field theory decomposes this into a sum over Feynman diagrams. String field theory does this by identifying certain string diagrams as elementary interactions, and the remaining string diagrams can be constructed by gluing these elementary string diagrams with string propagators. And using these elementary string diagrams, string field theory constructs an action for string theory. And the plan of the talk is to discuss an explicit characterization of the elementary closed string diagrams and describe the effective expression for quantum action for closed superstring field theory by exploring the hyperbolic geometry of string diagrams. And this talk is based on two papers I wrote with Syed Farooq Musawian, who is a PhD student at Perimeter Institute, and some papers that are going to appear soon. Now, an elementary string diagram is a string diagram that can't be constructed by gluing other string diagrams with propagators. Each elementary string diagram comes with a choice of local coordinate around the punctures and a distribution of picture-changing operators. And these local coordinates and picture-changing operator distribution has to satisfy certain conditions. First of all, the local coordinate that you choose must be invariant under the permutation of the punctures. And also, PCO distribution has to satisfy a set of conditions. They should be invariant under the permutation of NS and Raman punctures separately, and it should avoid the presence of any unphysical poles. Also, when you perform a large diffeomorphism on the string diagram, basically if you do a MCG transformation, the distribution that you choose on the string diagram must be invariant. Now, what is a closed string propagator? A closed string propagator is a specific gluing of two closed string diagrams. A string field theory glues two closed string diagrams by identifying local coordinates in the neighborhood of two punctures on two closed string diagrams using a special rule. So assume that you have two punctures P and Q. So first of all, you have to choose a local coordinate WP and WQ. Then identify these coordinates by saying that WP is equal to T by WQ, where T is a complex number e raised to minus S plus I theta. So you see that if you do this gluing, you are producing a family of string diagrams. And when S is greater than 0, this gluing corresponds to a closed string propagator having specific length S. Now we can consider set of all elementary string diagrams having handles H and m number of NS and n number of Raman punctures, and this set is called the string vertex. So you can't choose arbitrary string vertex. The string vertex has to satisfy certain condition. So when you do quantization of closed strings using BV formalism, it says that it imposes a geometric condition on the string vertex. So it demands that the string vertex, together with the diagrams that you obtain by gluing elementary diagrams using string propagators, must generate a single cover of the compactified moduli space. That means string vertices decomposes the moduli space into different cells, and integrating string measure over each cell corresponds to the contribution from a specific Feynman diagram. So here you have one example. So this is the moduli space of 4-punctured sphere. It has 4 different regions. One region can be filled with P-channel diagrams, and second region can be filled with U-channel, and third region can be filled with S-channel, but you are left with one region, and that's a string vertex. And the consistency condition that we should impose on the string vertex demands a specific condition on the choice of local coordinates and the choice of PCO distribution that you choose on the elementary string diagrams. So the continuity across the boundary of the string vertex demands that the PCO distribution and the local coordinate that you choose on diagrams that belongs to the neighborhood of the boundary of the string vertex must match with the induced local coordinate and PCO distribution on string diagrams with zero length propagators. So this is the continuity condition across the boundary of the string vertex. So to construct a consistent closed string field theory, you have to construct the complete set of string vertices. Using minimal area metric, you can do that. Minimal area metric is a specific metric that you introduce on a string diagram that has least possible area under the condition that all the non-trivial closed curves must be longer than or equal to 2 pi. Unfortunately, our current understanding of minimal area metric is limited, and you have to depend on numerics to explicitly construct this metric. So to get a calculable formulation of closed string theory, either you have to understand minimal area metric further, or you have to find a new construction for the string vertices. And I choose the second route. So we claim that we can construct complete set of string vertices using string diagrams with another metric. This is a hyperbolic metric. A hyperbolic metric has minus constant curvature all over the surface. So let me briefly mention some basic facts about the hyperbolic geometry of string diagrams. A hyperbolic string diagram with n punctures, h handles, can be obtained by considering action of Fuchsian group on the Poincare upper half plane. Poincare upper half plane is a plane with Poincare metric on it. And the isometric group of Poincare metric is the PSL2R group. So you can consider discrete subgroups and then act on the upper half plane and obtain a corresponding hyperbolic Riemann surface. And the nice feature about this hyperbolic string diagram is that if you have a diagram with h handles and n punctures, you can obtain all the hyperbolic metric on this diagram by considering a different geometric sum of 2h minus 2 plus n number of hyperbolic pair of pans. So what you do is you take a hyperbolic pair of pans and glue two hyperbolic pair of pans by identifying the boundaries that have same length. So at the boundary, you have a geodesy having specific length. And before you glue these two hyperbolic pair of pans, you can do a twisting. So that means at each attaching sides, you have two real parameters. Since you have 3h minus 3 plus n number of attaching sides, you have 6h minus 6 plus 2n number of real parameters. And that's the dimension of the moduli space of string diagram. Now, one more basic fact about hyperbolic geometry is that if you look into a neighborhood of a puncture on a hyperbolic diagram, and this region is isometric to a punctured disk with coordinate w and the metric that's shown here. And this is a hyperbolic metric on a punctured disk. And the claim is that, or you can start by defining a naive definition or giving a naive definition of string vertices. The naive definition is that so you consider a set of all inequivalent hyperbolic string diagrams having h handles and m number of ns punctures and n number of r punctures with no simple closed geodesy having length less than some parameter c star. So this is a parameter that I introduced. In the case of minimal area metric, this parameter c star was 2 pi. So still there also you can vary it, but here I choose an arbitrary parameter c star, and we have to assign local coordinates on these elementary diagrams. On each elementary diagram, we choose a local coordinate e raised to pi square by c star. This is a normalization factor, and then choose this coordinate w. So this is the coordinate that is induced from the hyperbolic metric on the string diagram. And we have to choose a consistent distribution of certain number of picture changing operators. So I can come up with any definition, but I have to show that this definition is consistent one. For that, we have to take this string vertex and then try to cover the whole moduli space using the string vertex and the Feynman diagrams that I can construct with this string vertex. So that means I have to see how string field theory is going to glue two hyperbolic diagrams. Unfortunately, when I glue two hyperbolic diagrams using string field theory, it introduces a collar on the string diagram that have some accumulation of curvature on a specific curve on the collar. So anyway, that means you are not able to construct hyperbolic diagrams using string field theory gluing. So anyway, you can go ahead and then study what is a local coordinate that is induced on a glued diagram. So we can calculate it, and that's given by hyperbolic metric multiplied with a certain correction factor. So the correction factor is 1 plus c star square divided by ln w mod of w, and then a coefficient y. And you have corrections that's of the order c star cube. C star is the parameter that I introduced for defining the string vertex. And this coefficient can be computed. So one can extract it from a specific combination of Eisenstein series. So that means the local coordinate that I introduced on the naive string diagram are not gluing compatible. So I won't be able to cover the whole compactified moduli space using this naive string vertex and Feynman diagram. But the good thing is that, so you see, the correction is of the order c star square. So if I can take the parameter c star going to 0 limit, that means I can avoid all the higher corrections. So I can avoid all the c star cube corrections, and then assume that the coordinate or the metric that is induced on the glue diagram is hyperbolic metric multiplied with this correction factor that's of the order c star square. And then what is the meaning of taking c star to be very small? That just means that I am enlarging my string vertex. So with this string vertex having very small c star, I will be able to cover most of the region in the moduli space. But still, we are left with some region near the boundary of the moduli space. So we have a notion of Feynman diagrams. So when you enlarge the string vertex, the good thing is that at the boundary of the string vertex, the mismatch between the local coordinates on the glue diagrams and the elementary string diagram is very small. So what I can do is we can choose a small neighborhood around the boundary of the string vertex and slightly vary the local coordinates on the string diagram such that when I reach the boundary of the string vertex, it will have the local coordinate that is same as the local coordinate on the glued surface. So that is a simple procedure. And we can do this because we know what is the explicit, in which way we are supposed to change the local coordinates. And if you are interested only in closed bosonic string field theory, this is a solution. So you can construct any string vertex using this procedure. And the good thing is that now we know how to construct these elementary string diagrams because we have a very well developed theory of hyperbolic geometry. So now if you want to construct superstring field theory, you have to mention in which way we are going to distribute picture changing operators on the elementary string diagram. So let me remind you that this PCO distribution has to satisfy certain conditions. First of all, it should be invariant under the action of elements in mapping class group. And then it should be invariant under the permutation of the punctures, NS and Raman punctures separately. And it should be compatible with gluing. That means it should satisfy the geometric condition that is induced from BV equation. So we can try to distribute PCO on a thrice punctured sphere. So this is the starting point. So we need to insert one PCO on a thrice punctured sphere if all of the three punctures carry NS states. We can think of a thrice punctured sphere as a pair of pans with vanishing border length. So let me provide you a distribution of picture changing operator on a pair of pans. So what we can do is we have to specify some location on which where we want to place the PCO. To do that, we can consider the fundamental domain for a pair of pans on the upper half plane, and that consists of two hexagons, two hyperbolic hexagons. And the PCO distribution that I want should be invariant under the permutation of boundary of the pair of pans, and it should be invariant under the exchange of two hexagons, because that doesn't change the hexagon. So the way is to choose the centroids of two hexagons, right and left hexagon. And the centroid has a nice property that when I exchange the exchange the boundaries, the centroid is unaffected. And when I choose two locations on one on the right hexagon and one on the left hexagon, I gain the symmetry under the exchange of right and left hexagon. So I can pick these 2 points, place PCOs there, and then consider an average. And this PCO distribution has all the properties. It's symmetric with respect to the exchange of boundaries, and also it's symmetric with respect to the exchange of right and left hexagon. This is known as the involution symmetry of a pair of. So you get a consistent distribution of picture changing operator by taking the border length to 0. So we can go ahead and see what's the PCO distribution on a once punctured torus. So let us try the same thing that we did for the thrice punctured sphere. So we can look into the fundamental domain for the thrice punctured sphere, once punctured torus on the upper half plane. So it's again same as a pair of bands. And then we can choose locations on the fundamental domain. But the unfortunate thing is that this prescription won't go well with the action of mapping class group elements. The reason is that let us go back to once punctured torus and then see how we obtain a fundamental domain. So we need to choose a simple closed geodesic on the once punctured torus and then cut the once punctured torus along that simple closed geodesic. And that gives us a once punctured sphere with 2 borders. Then cut the once punctured sphere to obtain the fundamental domain. So that means since there are infinite number of simple closed geodesic on a pair of on a once punctured torus, I can obtain infinite number of fundamental domains by choosing different simple closed geodesics. And all of these fundamental domains can be mapped to each other under the action of MCG. So if I want to distribute PCOs by choosing points in the fundamental domain, I also need to say in which way which simple closed geodesic I'm choosing to cut the surface. And that's not a MCG invariant information. That means the PCO distribution won't be invariant under the action of mapping class. So there's a simple solution. What we can do is we can take one fundamental domain, distribute PCO on that, like we did for the thrice punctured sphere, and then consider an average over all the fundamental domains obtained by cutting the surface along all possible simple closed geodesics. And the point is that all these simple closed geodesics are related by mapping class group transformation. So you can start with the one fundamental domain and distribute PCO just like what we did for the thrice punctured sphere, and then multiply with a weight factor. And the weight factor is a function of length of the simple closed geodesic and the twist that you perform with respect to the simple closed geodesic, and then sum over all the MCG elements. So usually, so this is an infinite sum. Usually this infinite sum won't make any sense because they may not converge. But if I choose a specific weight factor, which I choose the weight factor 2 sinc square tau gamma divided by 1 plus e raised to L gamma. The sinc square is a normalized sinc function, which is sine pi x divided by pi x. I choose this particular weight factor, and then the QC star is 1 plus 1 by C star plus 1 by 4 C star square. So if I choose this particular PCO distribution, this distribution is consistent because the weight factor, if I sum over all the elements in the MCG group, sum together to give you 1. And this is true because of the beautiful identity satisfied by simple closed geodesic on a hyperbolic once punctured torus. And this identity was discovered by McShane. And if I use, since I'm choosing this particular function, I have the McShane identity, and that tells that the distribution that I selected on the once punctured torus is a sensible, manifestly MCG invariant distribution. So that is fine. Now I have to check whether this PCO distribution satisfies the geometric condition induced from BV equation. So we have to see whether this is compatible with gluing or not. So for that, what we need to do is we need to check whether if we degenerate one of the simple closed geodesic, are we reproducing the PCO distribution that is supposed to be on the thrice punctured sphere or not? So again, we can utilize a nice feature of hyperbolic diagrams. So the feature is the following. So consider two simple closed geodesic, gamma 1 and gamma 2. So gamma 2 passes through gamma 1 perpendicularly. So if I degenerate gamma 1, the nice thing is that the length of gamma 2 goes to infinity. So using this fact, we can show that when I take the limit, when L gamma goes to the boundary of the string vertex, which is the limit L gamma going to C star, when I take that limit, the PCO distribution matches with the PCO distribution on a once punctured torus with a propagator having 0 length. And the correction is of the order C star Q. So this PCO distribution is a consistent PCO distribution that's manifestly invariant under MCG transformation and is gluing compatible. And the very nice feature of hyperbolic string diagram is that I can generalize this construction to any hyperbolic string diagram having arbitrary number of handles and arbitrary number of external functions. So we have a generalization of Machian identity on hyperbolic string diagrams. These string diagrams can have borders as well. So we can use identities due to Machian and Mirzakhani. And then if I use these identities, I can systematically construct a PCO distribution that's manifestly invariant under MCG transformation and gluing compatible PCO distribution. And the PCO distribution has this following form. So we have to start with a specific trivalent graph having h number of loops and m plus n number of external legs. So we can choose a specific PCO distribution associated with particular trivalent graph, and then sum over all the MCG elements, and then at the end, we have to sum over all possible trivalent graphs having h handles and m plus n number of external legs. And this is the form of PCO distribution. And if we use this PCO distribution and the local coordinate that I described you, we can construct all set of string vertices in closed superstring theory. And that provides a consistent closed superstring field theory for infinitesimal C star. And making C star very small is a valid operation because none of the physical quantities in string field theory depends on this parameter C star. So that means we get a consistent set of string vertices in closed superstring field. Now we can look into the quantum BV action for closed string theory. It has a kinetic term and infinite number of interaction terms. In each interaction term, say we are interested in the H-loop interaction term, then that's obtained by considering the H-loop optional superstring measure and then integrate this optional superstring measure over the region inside the moduli space that is covered by the string vertex. So you can take that integration, and since we are using a specific PCO distribution of this form, the nice feature is that the superstring measure becomes an object associated with a trivalent graph, and then sum over all possible MCG transformations, and then sum over all possible trivalent. So here, you can combine the sum over all MCG with the integration that you perform on a region inside the moduli space. And that makes everything simple. So it converts this into a real integral. A real integral, and then sum over all possible trivalent graph. And the real integral where you have integration over twist parameter running from minus infinity to infinity and length parameter running from C star to infinity. So this gives a a nice structure for each interaction strength. So this is the effective expression for quantum action in closed superstring theory. Now, if you are someone who is not interested in string field theory, you can utilize all this technique for studying string perturbation theory. So you can consider an on-shell string amplitude. For that, you can forget about all the details of local coordinates, and then take on-shell string amplitudes and choose the PCO distribution that I described to you. Anyway, that kind of a PCO distribution is necessary even for on-shell string perturbation theory. So take that PCO distribution, and the string measure is supposed to be integrated over the compactified moduli space. So if I choose the PCO distribution that I discussed, then again string measure can be converted into a string measure that depends on a particular trivalent graph, and then I have sum over all possible MCGs and sum over all trivalent graphs. So here again, I can combine the integration of the over the moduli space with the sum over all the MCG elements, and that converts this into a simple real integral. And here the integration is the twist integration is from -infinity to infinity, and the length integration is from 0 to infinity. So the nice thing is that now if you want to study string amplitude, you don't have to know anything about moduli. So you have a simple integral. And the whole difficulty will be just to construct the measure associated with each trivalent graph. So in summary, hyperbolic geometry can be used to construct calculable closed superstring field theory and provide efficient tool for computing amplitudes using superstring perturbation theory. And also, if you can generalize this whole story to the case of super moduli space, then it would be really nice. Thank you.
Questions?
Can you use this method to circumvent the usual problem to compute the homogeneous cosmological constant in the vacuum energy of the superstring?
Yeah. The only thing is that you have to construct the string measure. So once you construct the string measure, you don't have to worry about moduli.
Okay.
That's the.
I'll ask one. Do you perhaps as a test case you could do a low dimensional, a topological theory or a 2D gravity theory using these techniques?
Yeah, that's it.
Yes. Okay. If I'm not missing anybody and there's no more questions, let's thank again.
So now I ask everybody to orderly go out from the front entrance and then take photo. And please, speakers and chairs, please come toward the front row, which means toward the parking structure.
Andy Strominger was supposed to give a first talk, but unfortunately, he has not yet arrived. So the second speaker will give first talk. Thank you. So please.
Okay, thank you. Thank you very much.
Speaker is Yu Tin Huang, and his title of his talk is Inside the Walls of Positive Geometry, the Space of Consistent QFTs. So please.
Okay, thank you very much. First, I'd like to thank the organizers for giving me the opportunity to speak here today. I'm going to talk about some recent work in progress with Nima and Zizeng Huang, as well as some interesting and very exciting extensions done along with Shuhen Xiao, who spoke yesterday. So basically, the question that we want to ask is, what is the space of consistent QFT? So the operation word here is. Of course, consistent is, as usual, means that it is consistent with unitarity, locality, and whatever space-time symmetry we desire. And we will view this space or explore this space through the lens of physical observable. So since we're interested in general quantum field theories, we'll be interested both in the CFT and as well as the EFT along the RG flow. So for the CFT, the natural thing will be the 4-point correlation function, and for the effective field theory will be the 4-point S-matrix element. Now, looking at this through the lens of physical observable will allow us to explore the possibility of having new principle governing what that word is actually mean. Now, why might I expect that there's some new principles to be discovered? Well, because we've already seen this in the study of scattering amplitudes. So in the study of S-matrix for particular theories, recently we've realized that the notion of locality and unitarity has become really an emergent property. And it's been transcended by something that is more primitive, more fundamental in this case, which is the notion of positive geometry. An example of this is the now famous n=4 super Yang Mills, where the perturbative scattering amplitude is now given as a geometric object, which is the amplitude-hedron. And this is actually, now we've realized that this is not isolated to this particular theory. For the last year, people have realized there is actually a counterpart for even the simplest phi-cube interaction, where the tree-level amplitude is now given by what is called the associate hedron. So in this case, one might be tempted to ask, and you might say ambitious to ask, that is this positive geometry really actually not just applicable for these examples that we have found, but is an underlying property of general quantum field theories. Now, of course, positivity is not something new in physics. It's a very old concept that played many important roles. And in fact, for a long time, positivity is unitarity. So for example, in the discussion of 4-point correlation functions for identical scalar operators, as an example, when you expand on a conformal block, unitarity tells you that this expansion has to be a positive expansion, this coefficient, which is basically the square of 3-point OPE coefficients is positive. We can go even more further in the older days where we are in the textbook, we see that we've learned optical theorem, which tells us that the discontinuity of the 4-point interaction in the forward limit is proportional to the total cross-section, which of course is positive. So this is nothing new. And not only is this nothing new, okay, so not only is this nothing new, but this notion of using positivity to carve out the space of consistent QFT is also nothing new. This is exactly what has been done in the past few years in the Bootstrap program. And for the old the optical theorem story, that people have already used this to bound coefficients of certain higher dimension operators to be positive before. So this has already been done before. So what more can we ask for? Well, actually, the question is the opposite. We should expect more. And the reason that we should expect more is because in these discussions, so the functions that are involved are very special functions. These are functions that are being constrained by factorization and symmetries. So for example, for the CFT, we have the conformal blocks. These are special functions. These are solution to conformal Ford identities. They satisfy differential equations. Now for general quantum field theory, the discontinuity of the 4-point functions, we know that it should be expandable on the Gegenbauer polynomials. And Gegenbauer polynomials is also something very special. And you can interpret the definition of this polynomial as basically the scattering of four identical scalar exchanging a spin L particle. So these are special functions. So we should expect that we would explore that this space that are constrained by the properties of these functions to be special. So let's begin this exploration. So let me first begin with the EFT part of the story. So here's my general setup. So here I'm going to consider a general quantum field theory. And I'm going to assume that it has some UV completion that is unitary. Now, first of all, the UV completion, I'm going to assume that it is weakly coupled and in Planck. So I'm just doing this because I'm considering a low energy effective theory, which involves masses, gravitons, and photons. And I want to have a perturbative parameter to suppress my massless cut. So if I can suppress my massless cut, then that means that the 4-point function in the complex S-plane around the origin is just going to take this simple form. It's going to have some massless poles. And it has some expansion in terms of small s and t with some non-trivial expansion coefficients. So these are basically the coefficients associated with the higher dimension operators. So different quantum field theories in this language is translated into the different numbers that you can have for the set of this coupling constant. For example, the standard model, when we go to ultra low energy, we can compute all the higher dimension operator involving the photons, so which would be encoding the information of the mass and the charge of the massive particles, and these will feed into what these coefficients precisely are. So naively, we would say that these coefficients in principle from the low energy point of view can be arbitrary. And you might ask, so why might one expect that this space to be non-trivial? To see why, first of all, so first of all, let's just focus in 4 dimensions. All of this discussion, it can be applicable to any higher dimension. So I'm just focused in 4 dimensions. And in that case, the Geigenbauer polynomial is just the Legendre polynomial. So in this very simple context, we know that away from the origin in the complex S-plane, we're going to have the possibility of massive poles and then massive branch cuts. So here also for simplification, I'm just going to assume that we have these poles in the S channel. I'll talk about generalizations to both S and U channels later on. Okay, so as I previously said, that we know that the residues and the discontinuities has a positive expansion on the Legendre polynomial. That means that the function, the 4-point function away from the origin will take this simple form. So it has some sum over Legendre polynomial, where the entry, where the argument now, instead of the usual cosine theta, I'm writing in terms of Mandelstam variables. And of course, you have the propagators that are here. If it's a branch cut, then you just have something that look like a propagator, but just integrated from the branch point upward. But it basically takes the same form. Now, so once we know that we have this form, we can just do a stupid Taylor expansion, and then basically it predicts that the Taylor expansion has this form. So the statement is that these coefficients are directly related to the UV completion, including the mass and what the 3-point functions, 3-point coefficient are, which tells you that this is positive, and this vector here, this U vector here, which is coming from both the expansion of the Legendre polynomial and as well as the expansion of the propagator. So just to make this more geometric, so let me organize my coupling constant in this way. So I have the horizontal, which corresponds to which mass dimension these coefficients corresponds to. And for the vertical, it corresponds to how far away from t equals 0. So this is different degrees in t. So this will be basically an expansion around the 4 limit. So I'm going to organize my coefficient in this form. So once I'm organized in this form, then I can look at this equality upstairs. And for example, let's look at the mass dimension 8 operators, which correspond to these 3. So there's 3 different distinct structure. This corresponds to S squared, this is ST, and this is T squared. So we have these coefficients here. And the equation on the right-hand side of the equation, we basically have that it's given by this U vector here, which I also organize in terms of U0, U1, U2, corresponding to different powers of P here. And this PA prime is just the original PA, but with the mass absorbed. Now, since PA is positive and the mass, we assume that we have positive mass, so that means that this PA prime is positive. So if I organize it in this form, you see that this is a non-trivial statement. The statement is that these three coefficients form a vector, and this vector is sitting inside the convex hull of these vectors that are coming from expanding the Legendre polynomial and propagators. The convex hull of a set of vector is what defines a polytope. Okay, so that means that there's a polytope in this problem. Just to give a brief review of the polytope, so let's discuss the two-dimension simple case. So the two-dimension polytope will be like basically a polygon. One way of saying what is inside this polygon is basically what we learned in middle school, or even elementary school, which is basically we consider the center of mass. The center of mass will always be inside. So this is the way that we would compute the center of mass, which is the vectors weighted by some positive coefficient. And of course, this will be just an overall normalization factor. So this describes the inside of a polygon. And of course, this can be generalized to arbitrary dimensions. You basically just generalize this vector here. So it turns out that it's actually more easily to write things projectively. So we embed this in one dimension higher. Then this inside of the polygon becomes what is mathematically defined as the usual definition of convex hull, where basically we have a vector here, which is given by a linear combination, a sum of these vectors with positive coefficients, and the coefficient sums to 1. What determines what is inside, for example, for this case, is basically you determine first which of these vectors form a boundary, and what is inside is then the requirement that you take the determinant of the two vectors that form the boundary, along with whatever you have, whatever vector you have, and if it's inside, then that this determinant will have a positive number. So from this, you can see that to determine what are the boundaries is basically to determine all the possible signs that you have for these vectors for the determinant. So we basically have a problem of that we want to understand whether or not something is inside a polytope. Now, if these U vectors that was coming out from expanding the Legendre polynomials are just a random vector, then this is basically a hopeless problem. There's really, even though I make it sound very nice, we say that these coefficients, these coupling constant has to be inside a polytope, but this is actually practically a useless statement. To see why it's practically useless is because basically we have this vector, and if we really want to decide whether or not something is inside, what do you need to do? Well, first you need to decide which of these vectors are actually form the vertices of this polytope. Once you know which ones are the vertices, then you need to determine what are the boundaries of this polytope. Now, this computation is basically, for example, for the previous two-dimension problem, you basically need to collect all of these vectors, collect them in pair, and then if you take any pair of these and then take the determinant of this pair with any other vectors, if these two form a boundary, then this determinant will be always definite positive. Will be positive greater or equal to 0 for all i's. So you need to do this computation. And as you can see, that this computation basically scales polynomially with the number of vectors you have. And the number of vectors we have for our problem is infinite. Okay, so even though I'm stating it as a very interesting statement that this has to sit inside a polytope, but this polytope has the number of vertices that are infinite number of them. So in principle, this is application-wise, this is a useless statement. However, as I alluded to in the beginning, these are not random vectors. These are vectors that are coming out of some very constrained functions. So let's look at what these vectors look like, actually. So again, we have this 4-point function written in terms of possibly infinite sum of the Legendre polynomial over the propagators. So let me just expand this polynomial, Legendre polynomial, and let me define this vector v here, which corresponds to expanding the Legendre polynomial around the 4 limit. So I've explicitly given you the explicit form of these vectors, or the explicit numbers. So this would be the spin 0. So there's no expansion for spin 0, spin 1, spin 2, spin 3, and so on and so forth. So these are just numerics. You can just put it on Mathematica and just expand it. And of course, the first thing you'll notice is that all of these numbers are just positive numbers. Okay, so that was just a reflection that the derivative of the Legendre polynomial is always positive when you evaluate at 1. And in fact, this is already true. That this is already a fact that is known during the 60s. And this is also true for general Eigenbauers in any dimensions. But the statement is that there's more positivity than this. if you take this matrix and you take any ordered minors inside it, you can just take any ordered minors, n by n minors, and you just compute the determinant, you'll realize that it's always positive. Okay, this is always a positive number. And this positivity is extremely non-trivial because, of course, when you're taking any determinant, you're taking the plus and the minus of various terms, and somehow the plus and minus always adds up to a positive number. So, in other words, the minor of the vectors, the Gegenbauer vectors, is always positive so long as you order the spins. So this immediately tells us that our problem is actually solved. There's nothing to solve. So when all of the vectors are positive, have positive ordered minors, that means that these vectors actually, the convex hull, form what is called a cyclic polytope. A cyclic polytope tells us that all of the vectors are actually, all of them are vertices. And actually, all the boundaries are actually just given to you directly. So for example, or when the dimensions is even, the boundaries are just I plus 1 for the 2-dimension case, I plus 1, JJ plus 1, and generalizations for higher and higher dimension. For all dimensions, exactly the same pattern. You just have an extra vertex at 1 and extra boundary by adding 1 and the last entry, but in our case, it will be infinity. So there's no computation to done. You know what the vertices are, and you know what the boundaries are. And this is boundaries of all dimensionality. Okay, it's just from the very fact that this is a cyclic polytope. And indeed, for the Gegenbauer expansion, the Gegenbauer vertices form a cyclic polytope. But unfortunately, and actually fortunately, the vectors that we're interested in, U, is not strictly speaking V. So if we track this through, remember that when we're expanding the Legendre polynomial, we get these vectors V. But there's also an expansion in terms of the propagator, which gives us another polynomial here. So the blue part is what is coming out of the Legendre polynomial, which is basically a statement about unitarity. The red part is expanding the propagator, which is a statement about locality. So let's, for example, let's focus again on the fixed mass dimension. Now, fortunately, for the fixed mass dimension, so basically, since so we're looking at each order in the expansion of T. Each of these are then multiplied by the appropriate factors of S factor to form the correct mass dimension. But luckily, all of these coefficients are just 1 here. And therefore, it's the coefficients for this product of the fixed mass dimension is still basically just the Gegenbauer vectors. So indeed, we do have that the Gegenbauer vectors, the boundaries of the Gegenbauer vectors, is bounding the vector that are associated with fixed mass and then further T expansion. So for example, directly already for the mass dimension 8 operator, I can say that it must satisfy the infinite number of positivity condition, which you just take the Gegenbauer polynomial and expand out for different spins. And for adjacent spin, when it dotted into this 3-dimension vector, it must be positive. So there's an infinite series of constraints already. But of course, we can look at things horizontally, and we can also look at things, vertically, we can also look at things horizontally. If we look at things horizontally, then since all of these Gegenbauer expansion vectors are just positive numbers here, that means that for fixed T is just a positive number multiplied by these are also positive factors here. So that means for the fixed T vector, if I collect them together, these are actually coefficients for higher dimension operator of different mass dimensions. So these different mass dimension vector now again sits as a convex hull of this interesting vector here. And if you look at this, it turns out that this vector just basically tells you that these coefficients is sitting inside the convex hull of points on a half moment curve. So basically, a moment curve is just a 1-dimension curve in n-dimension space, which is parameter. Each entry is basically different degrees of x. And we call it a half moment curve because here x must take value and with a positive number is just because that the mass is positive. So this is another positivity coming from the propagators, and we can deduce what the constraint of this positivity is, and that is simply that if you organize these couplings here. So these couplings here, since they all have the same power of T, so I can suppress this T factor here. So let me just call it G prime. So G prime, I've suppressed the factor of T. And then you organize the G prime in this fashion into what is called a Hankel matrix. then the statement that if something is lying in the convex hull of this half moment curve becomes the statement that the Hankel matrix has always have positive minors. And we can prove this analytically. So for example, all of these minor with different G order powers of G, they will always have positive determinants. And you can take the subminors and they're also positive. Just to show you what is the power of this positivity constraint from the Hankel matrix. So imagine that you have some massive vector here, and then coupled to gravitons, and I'm computing the one loop effective action. So I can compute the amplitude expand out in terms of large mass expansion. And the forward limit, because I just want to capture the powers of S, there's a closed formula for the coefficient. So you can imagine, so let's just imagine you don't know what the leading coefficient is, and you just know the remaining coefficients. Then you can plug the remaining coefficients into this Hankel matrix, and positivity and unitarity tells you that this Hankel matrix has to have positive minor. And that constraint bounds this first coefficient. And so this is how the lower bound on this coefficient. And you see it's asymptoting to a fixed number, and this fixed number is basically exactly the exact number that you have in the beginning. Okay, so this is a very useful constraint. So what is the story so far? So the story is basically that unitarity locality and Lorentz invariant is telling you that the effective field theory is actually the coefficients of the effective field theory are actually a union of two kinds of positivity. There's, from unitarity, it tells you that the expansion in T is giving you, requiring that it's something that is inside the convex hull of cyclic polytope. And from locality, it's telling you that it's inside this convex hull of a moment curve. These two combined tell us that there's a new notion of positive geometry, which is a generalization of polytope, and we call this basically the EFT hedron, because this is motivated by the EFT. So remember that polytopes are basically the convex hull of vectors. Cyclic polytopes are convex hull of vectors, where the vectors, for all ordered vectors, these have definite positive determinants. What the EFT hedron is that it is again the convex hull, but not just in terms of positive number, but weighted by this positive number, where this positive coefficient must have that it form a Hankel matrix whose minors are always positive. So this is the definition of the EFT hedron. So in other words, the IR avatar of UV local and Lorentz invariant UV completion is the EFT hedron. So this is basically the answer to what the question that I posed in the beginning. What is the space of consistent QFTs? Of course, this is, let me just skip this in light of time. Of course, there I made an assumption that I only have S-channel poles. You can generalize this to any interaction which involves U-channel poles. And actually, the fact that you want to generalize to involve U-channel poles actually explores something more. So if you involve the U-channel poles, then you have the U-channel contributions here. And again, you do exactly the same computation. You expand out and expand the Taylor series. You'll see that now the U vectors is actually a linear combination of the original Geigenbauer vectors, but with minus signs. So naively, you'll think that now everything is out of the window, because if I compute the ordered vectors, it's going to be given by a sum of different terms, ordered Geigenbauer vectors, but with plus and minus sign. But if you have a little bit of faith, you would actually compute this, and you realize that this is actually still positive. And this positivity is actually probing something more, and that is the statement, or actually it's positive above a critical spin. But this positivity is really exploiting that these minors in the Geigenbauer vectors actually have a hierarchy, in the sense that the evenly spaced minors is always the largest, the maximal minor compared to all the other minors. So again, since it's still a cyclic polytope, so we can easily determine what the boundaries are. And also, there's also a similar statement for the moment curve constraint. And the moment curve constraint now also becomes more interesting, because it becomes the Minkowski sum of different moment curves. And that means that the constraint, it corresponds to a generalization of moment curves, where the moment curves is deformed by a rescale parameter, where the rescale parameter now depends on the specific dimension that you're looking at. And you can also generalize this. So I've discussed this in terms of scalar particles, but you can also discuss this for spinning particles. And everything is exactly the same. We still have this cyclic polytope. The only thing is that you need to change is that you need to change the Geigenbauer polynomial in terms of the Wigner-D function. But the entire geometry still goes through. Okay, so this is just giving you to see a shape of, this is the gravity, this corresponds to the polytope associated with the scattering of 4 gravitons. And yes, as you can see, that this is approximating attending a moment curve. So I guess I still have only 5 minutes left, so let me just go very quickly to the CFT problem. But for the CFT, you know that this is exactly the same structure, which basically you have the 4-point function. You're expanding on the conformal block. You can take the conformal block and then make a Taylor expansions, and then you will get a Taylor series expansion. You get some vector. Now, of course, we have crossing symmetry. That just means that the 4-point functions is lying on a subdimensional plane. Oh, okay, to finish. Okay, sorry. Okay, so just the punchline is basically that, again, this is a cyclic polytope. The vectors coming from the conformal blocks are actually just cyclic polytope. And that means that you already know what the boundaries of the cyclic polytope is. And you can easily carve out the space of consistent CFTs. So this is just a plot of the cutoff from the dimension of the first 2 operators. And you can go, there's a lot of simple geometries to using this geometry to understand the space properly. So let me just skip all the way to the end, sorry. So the punchline, I think the punchline of my talk is basically the constraint of unitarity on locality and symmetry. Now we can see that it actually manifests itself as the positive geometry in the space of consistent QFTs. In the story of effective field theory, it corresponds to the space of consistent coupling. And that space is basically what we define as the EFT hedron. For the CFT, the space is given by the combinatorics that arise from the intersection of the crossing plane along with the cyclic polytope. So there's a lot of important questions to ask. For example, to explore the EFT hedron in the SU channel basis. We want to explore more involving the mixed interaction of graviton and photon, which might have something to say about the weak gravity conjecture. And of course, for the CFT side, we're now only just solving the 1D CFT geometry, and there's really the whole slew of questions to be asked for higher dimension CFT. And even for the 1D CFT, we should push this geometry to higher dimension, where higher dimension corresponds to how far you're expanding in terms of the Taylor expansion. So this is the end. Thank you.
Okay, thank you very much. We have a couple of minutes for discussions. So any questions or comments? So please.
When you have degeneracies of mass levels, like in string theory, just requiring the positivity of the 4-point function residues, it's not enough.
Yeah, I mean, here we just
to be sure there are no negative norm states all the way, and you have to disentangle the degeneracy.
Well, here we're just well, I mean, the degeneracy for us is basically fine. I mean, basically here we're just saying that you have positive. The only thing we're using is you have positive mass, and you have the expansion is always unitary, so you have a positive expansion, and that the UV completion is Lorentz invariant, which dictates that the point.
We may have degenerate level.
Yes, we can have degenerate
negative
level.
Norm. Theory is system.
Right.
It was the ghost killing problem.
But you can do the analysis for the O-string theory, and then you can see.
There's another way of putting this. You're considering 4-point functions of scalar fields. You're looking at contributions of spin J fields, right, which might be degenerate. Now, in any reasonable theory, those spin J fields are going to interact with themselves.
Right.
And until you look at the n-point function where n is arbitrarily large,
right,
like a million or infinity, you can't really say anything.
Yeah, or the other thing is to put these massive fields on the outside of the 4-point function.
you could put them on the outside of the 4-point function.
And ask for the consistency of that.
Yeah. But you're discovering, you're putting constraints on the contributions of spin J fields, which might be, there might be an infinite number of them for all you know. You have no idea.
Yeah.
The real constraints can only come, as they did with the Veneziano model, the dual resonance model, eventually string theory, by considering the constraints arising from n-point functions where n is not just 4, but infinite, arbitrarily big.
Yes, and
that is an infinite set of extra constraints, in addition to those that come from the 4-point function.
Right. So,
in
but
the
even
case, the historical case of the dual resonance model, the 4-point function positivity was trivial.
Well, I mean, even
n-point constraints led to a unique theory.
Sure. I mean, but even at just the 4-point function at the discussed, you will seem that I have an infinite number of constraints because I mean they have the number of boundaries are infinite. But as in the 4-point function, you usually see you have infinite number of constraints. But when you look at it, it's really, you can identify what is the stringent constraint, and these are a statement of geometry that we can identify. So as I mentioned in the second part, where you can actually have spins on the outside. So I would expect that we can analyze the constraints coming from the spins on the outside and looking at whether or not we can identify that there's actually a subset of the constraints actually more stringent. Well, it's just that the functions that are involved now are are no longer unique functions. So we don't have a functional basis to expand the endpoint function. That's maybe one way to say it.
Yeah, unfortunately, time is running out. So if the question is very short, maybe we can accept one. Okay, is it short? Okay, sure.
The answer doesn't have to be short.
Answer should also be short.
Yeah, just a small technical question. You implicitly assume that the amplitude decays faster than a constant.
Yeah. So
wait, just a second. The question is, on the other hand, when you analyze the scalar coupled to gravitons, there was a constant piece, so it was contradicting your initial assumptions.
So you mean the Hankel matrix constraint where I was getting the first contribution? Yeah. Also, I should mention that because the graviton, I'm actually factoring out the spin distribution in front. So that means the remaining piece. So I'm actually not the full amplitude, but I already factor out that basically r to the 4 piece in front. So that means that the remaining piece will be decaying faster than the constant. So that's why I can get that bound.
Okay, so time is running out, so let's thank the speaker again. Thank you very much. So next speaker is Andy Strominger. He has arrived, so please. So he'll tell us about progress and questions in soft physics in memory of Stephen Hawking. So please.
Hear me? Okay. First, I want to thank the organizers for a wonderful conference, and especially Hiroshi for arranging a wonderful hotel. So wonderful that I slept for 16 hours, which I've never done. Which I've never done in my life. So it should be a great talk. Okay. And sorry for being late. So I'm going to talk about a number of different things that I've been doing related to soft physics and large diffeomorphisms or large gauge transformation, and related to both theory and experiment. And so perhaps the first topic is the idea of flat space holography, which concerns the deep infrared far from the interior of the space-time. And the first idea about this is in a very prescient paper of Bohr and Solodukin from 15 years ago. And the simple idea was to take flat space and slice it in Euclidean ADS3. Only in a string conference do you refer to a hyperbolic plane as Euclidean ADS3. Euclidean ADS3 and view Minkowski space as a kind of non-compact compactification over ADS3. And they looked at that and then said, hey, that's ADS3. This is DS3. And therefore, there should be a three-dimensional one. There should be a Virasoro algebra appearing there. And that was kind of a wild conjecture, but it turns out to be true. And this is DS3. And so they had two conformal field theories, one down here and one up here. And they wanted to have a map from one to the other. Now, since then, we've learned two important things. The first thing is that the conformal structure of this sphere, the sphere that lives at the boundary of this EADS3, is rigidly tied to the conformal structure down here. So there's only one sphere. There's only one set of conformal transformations. And moreover, we've proven that those conformal transformations do exist. We didn't just conjecture it. That is a soft theorem that Cacciazzo and I proved some years ago. So it is true that you can take, for quantum gravity, the S matrix of 4D Minkowski space and rewrite it as a correlation function of some kind of exotic CFT2. So this CFT2, as we'll see, has imaginary weights. It's not the usual garden variety CFT2 we are used to, but it is an object that transforms under two copies of the Euclidean conformal group which act on this boundary. And in particularly, ordinary Lorentz transformations, which is SL2C, is the global conformal group of this two-dimensional sphere. Now, just as far as that global conformal group, there is nothing conjectural or mysterious about this. It is an algorithmic thing to do to write any S matrix of any theory in a basis in which the Lorentz transformation is manifest. What is a conjecture is that there's some independent, not just that the right-hand side is defined by the left-hand side, but that there might be some interesting intrinsic way of defining the right-hand side. That we don't have. Okay, so in the last year or two, there have been some interesting works starting to make baby steps to understanding what this two-dimensional conformal field theory could look like. So usually, you write everything in terms of plane waves when you do scattering amplitudes. But plane waves are nasty when it comes to SL2C. They don't transform nicely under SL2C. They aren't eigenstates. They transform into one another. What you want is to take SL2C. If you have a particle that comes out at some point, there's an SL2C. There are many Lorentz groups inside the Poincare group, and there's a special SL2C in which L0 is boost towards that point on the sphere. L0 plus L0 bar is scalings, boost towards that point. L0 minus L0 bar is rotations around that point. And for a primary, L1 will annihilate those points. So the project was to find the primary wave functions that obey all these conditions. And in a beautiful, there's a number of papers on this. This isn't even really all of them. Bohr and Solodukin talked about pieces of this discussion, but it's also all beautifully summarized in this paper by Pistersky and Shao, in which they find the complete set of conformal primary wave functions. And by complete, I mean that any set of plane waves can be rewritten in terms of these, which, for the case of a scalar, a photon, and graviton, which I guess is on the next page. And what you find is that for a scalar, the highest weight, h and h bar, are equal. They're 1 plus I lambda, where lambda is a real number. This is called the unitary principal series. And interestingly, for massive fields, lambda can be any real number, but for massless fields, lambda has to be a positive real number for massive, and for lambda it can be any real number. So when you look at it this way, in the usual momentum space presentation, the space of massless states lies on a light cone, and massive ones lies on a hyperbola. There's no meaning to the question, is the hyperbola bigger than the light cone? But in this basis, you can see that there is some sense in which there are twice as many modes of a massless scalar field than there are massive scalar fields. It's really a pretty discontinuous limit. For a photon, h minus h bar is 1. And I could have the other helicity too, but it's 1 plus I lambda, again, lambda in real. But you need to look carefully at the case lambda equals 0. So there's a Hermitian product that comes from the Klein-Gordon product that pairs 1 plus I lambda with 1 plus I lambda. And there's a delta function. But something funny happens at lambda equals 0. There's a delta function of lambda and minus lambda. But at lambda equals 0, something funny happens. It can't be paired with itself. And there's a kind of logarithmic branch in the solution space. And it turns out that there's a second mode. So you have two modes. And we, in recent work, partially in Pistarsky and Shao, and also in recent work with Nane and Hume, we've found that there's two modes, which are the conformally soft photon. Now, the idea of a conformally soft particle is an interesting one. So usually we talk about soft particles where the energy is 0. But when I say conformally soft particle, I mean a particle which transforms as a current under the SL2C on the sphere. And the fact that it transforms as a current will automatically introduce all kinds of constraints on its possible correlation functions / S matrix amplitude, scattering amplitude. So there's two currents. They're symplectically conjugate, the conformally soft photon and the Goldstone boson for large gauge symmetry transformations. And the conformally soft photon has the level is 0. The level of the conformally soft photon with the Goldstone boson is 1. That's really just a matter of normalization. But interestingly, already something interesting is happening at the free level. The level between two Goldstone bosons is, in fact, the cusp anomalous dimension. So there's an interesting number now that appears in this calculation. It's not just calculations of solutions of the free wave equation. And we'll see that that plays an important role later on when we use these to construct scattering amplitude. The graviton is even more subtle. Again, now we have 3/2 plus I lambda and -1/2 plus I lambda. And when lambda goes to 0, again, you get a log branch and you get two modes. One of them is the Goldstone mode for broken supertranslations, spontaneously broken supertranslations. And the other is the generator. The analog is essentially the soft graviton, which generates supertranslation. And now something really funny happens. If you take lambda to be complex, you get a field of dimension 2, 0. And that field of dimension 2, 0, right now we're just talking about wave functions. But if you convolute it with the Bondi news, which is the field operator now we're constructing a field operator, and insert that in correlation functions, this weird looking expression, which appeared some time ago in a paper by Dan Kapitz, Prahar Mitra, Ana Reclario, and myself, we derived this expression in a very different way by reverse engineering the subleading soft graviton theorem that Chazo and I had. This simple object, if you insert it in any correlation function in the sphere obeys exactly the Ward identities of a two-dimensional stress tensor in a conformal field theory. So this is the object, the 2-0 component of the graviton that computes the Ward identities of the stress tensor of a two-dimensional conformal field theory. And that's how we know that the conformal field theory that lives on the celestial sphere that describes any theory of gravity. And by the way, I want to stress that everything I'm saying is completely universal. It applies to string theory, it applies to loop gravity if it exists, it applies to any theory of gravity, obeys the identities of a two-dimensional conformal field theory. Okay, so we really don't know what the lay of the land is here. And we tried to do some simple calculations, which turned out to be mathematically harder than we expected, of just some simple correlation functions. And the first thing we did was just to compute the 3-point function of some massive scalars. Now, if they all have the same mass, 3-point functions are a little bit degenerate. So it's a kind of tricky thing to do, but the mathematics was simple, even if the physics was a little hard to compute. We computed near extremality, where if all masses are equal, the kinematics prevents any kind of decay. And we took this ordinary scattering amplitude and reinterpreted it as a 3-point function on the celestial sphere. And indeed, we found some constant involving a bunch of gamma functions. And it takes the standard form of the 3-point function. And by the way, I didn't say this explicitly, but there's a map between the p's and the z's. The z's, there's an explicit formula of it. It's basically z equals p1 plus ipt, p1 plus ip2 over p3 plus p0. It's the point at the sphere to which a field of momentum p asymptotes at late time. And the correlation function indeed takes this form that you encounter in any chapter in a conformal field theory book. Now, and this has to be true, an exact statement. This denominator has to be exact to all orders in perturbation theory. But computing G, the constant up here, especially at the order of loop amplitudes, can be a pretty arduous exercise. We just did tree level. There's been some start on loop calculation. Now, one of my favorite calculations, which I've actually never given a talk before, even though it was a year ago, is that in the last several decades, it's been shown in QED and also in QCD that the total scattering amplitude in momentum eigenstate factorizes with the help of an infrared divisor into a soft piece and a hard piece, where the soft piece contains all the soft and collinear poles. Now, if you think about it, we've seen something like this before in two-dimensional CFT. If you have a two-dimensional conformal field theory with a current algebra, it factorizes into a current algebra. Any old correlation function factorizes into a purely current algebra piece involving the currents and the U1 bosons, and this, which I don't know what they're called now. Gettner called them parafermions. And these are non-local operators where essentially the original operators with the U1 boson piece stripped off. And so there's this universal piece and a more complicated piece. And this is the hard piece, and this is the soft piece. Now, you might wonder how this simple current algebra, which involves 1 over z minus w, turns into this very complicated formula for the soft piece that was derived after a decade of work in QED, which involves Cauchys and and invert hyperbolic tensions of quotients of products of momentum and so on and so forth. And that just had to do with standard stuff that is now standard in ADS-CFT of bulk boundary propagators, which appear in this calculation and so on. So you start out with some simple calculation involving 1 over z minus w's, and you transform it in using the algorithmic method of transforming to correlation functions for massive particles, and you get, lo and behold, exactly this formula for the soft factor of the S matrix. And in fact, we found a new generalization of it, including particles which had not been known before, including the case where there are arbitrary magnetic charges on the asymptotic particles. MHV amplitudes have also been looked at. We computed them to 3 points, and Schreiber, Volovich, and Zlotnovic computed the endpoint amplitudes, and they're given by Amato, Gelfand, generalized hypergeometric functions on the Grassmannian GR4N. And now, in this case, it turns out that there's a Katz-Moody symmetry on the sphere related to the group G of the Yang-Mills theory under question. And it would certainly be interesting, there's a big formula sitting there, and the symmetry of which we haven't yet gotten to the bottom of. So I do want to emphasize open question because this field is just overflowing with open questions. What we're doing is taking very baby steps and trying to build it up into some bigger picture. What are the kind of open questions where we're going? Well, first we'd like some really simple example, free field theory or something, where in some approximation, probably not exact at the first crack, we have an example of a two-dimensional field theory with an intrinsic definition which reproduces a four-dimensional S matrix. Now, these are not exotic garden variety CFTs, but they have some very good properties. The S matrices which they produced, interpreted as four-dimensional S matrices, obey unitarity, crossing symmetry, all the good properties of four-dimensional S matrices. And those good properties, things that we know exactly about these putative 2D CFTs, must translate into some good properties of the 2D CFTs. They're just not exactly the good properties that we're used to. The good properties that we are used to exclude things like complex conformal weights. And I think that is an algorithmic question. Now, here's one of the things. I'm saying that the four-dimensional S matrix in every quantum theory of gravity is computed by some kind of two-dimensional CFT. This statement may have a familiar ring to it because, after all, the string world sheet is a two-dimensional CFT which computes the S matrix for a 4D quantum theory of gravity if it's a compactification to 4 dimensions. And so there must be some kind of relation between them. And indeed, there's what looks to me like a very beautiful paper from last week, which I haven't fully digested, by Stieberger and Taylor, in which they compute the string amplitudes as correlation functions, as they turn them into celestial correlators, and they find some very interesting answers. One of them is that there's a limit of large conformal weights in which they reduce, is that, did I start 5 minutes? I started 5 minutes late. Oh, I have 10 minutes, okay. And okay, it's a great paper, read it. Okay, we need to do the same thing for gravity, the celestial through the soft factorization. And then there's also the question of, once you write as a current algebra, there's this thing of enhancement. Is there some kind of strong coupling enhancement of U1 to SU2, as suggested by the current algebra? It's strong coupling, something very interesting happening in ordinary QED. It's strong coupling. Next, I want to talk about progress briefly about progress with Stephen Hawking and Malcolm Perry and Malcolm's student Sasha Heiko about black hole entropy and soft air. Now, we're used to the idea of a near horizon scaling region, and that is the only trick that we have for understanding black hole entropy, where you have a black hole and there's a near region in which there's some kind of emergent conformal symmetry, and we use that to deduce something about the entropy. Not all black holes have the property, so we need to find more tricks. Now, one of the things is that all black holes have an emergent conformal symmetry, which is not in a region of space-time, but in a region of phase space. And it's in the region of phase space where the excitation of the black hole has a wavelength large compared to the radius of the black hole. And this was discovered about 8 years ago, but we didn't know quite what to do with it then. And the best way to see this is if you look at the near region contribution to the scattering amplitude of the black hole, you find this formula, which is on the nose, the formula for a absorption cross-section in a thermal two-dimensional CFT, and you can moreover read off it what the conjugate, what the temperatures and what the conjugate energies and potentials are. And so there's something thermal going on in this region of phase space, but it's not, there's something conformal symmetry acting in this region of phase space. And another way of seeing it, which was really first pointed out long ago by Finn Larson, is if you solve the near region wave equation, the conformal symmetry can be seen from the fact that the near region solutions are hypergeometric equations, which are representations of SL2R. So now we have a new perspective on black holes and black hole horizons, in part from our work with Hawking and Perry. And what we found is that explicit in our draft, it's a completely explicit pair of vector fields which obey two Virasoro algebras and use precisely and realize this hidden conformal symmetry. But now we know, using the Ayer-Lee-Wold, I forgot poor Mr. Zupas, formalism, how to compute the central charge of a Virasoro algebra with a boundary using their surface term. And we use that, and we find that the left and the right central charge are equal to 12J. And if we put this all together and assume the Carty formula, we get exactly the area over 4, suggesting that this kind of analysis of large diffeomorphisms near a generic soft hair, near a generic black hole, can be inferred, that the entropy can be inferred from their action. And I just want to say that during the end of his life, Stephen wasn't able to use his typer for the last 2 or 3 weeks, but according to his nurses, his very last expression before he passed away was a huge smile when we came across this result, just like 5 days before he passed. Okay, I only have 5 minutes. I'm not talking about all the questions. All right, so the last thing I'm going to talk about, again, it shows the breadth of these infrared things, is color memory, which my collaborator at Brookhaven, Mr. Venugopalan, has become very excited about. An experimental application, which Monica Pate talked about during the Gong show, of some of these ideas about soft physics. So in classical gravitational memory, you have a pair of nearby detectors, the wave comes by, they oscillate, and at the end of the day, they don't get back to where they came from. In color memory, you have a pair of quarks, the arrows are going in different directions here, red and anti-red. A color wave comes by, they oscillate, and they're no longer in a color singlet. That's color memory. just like gravitational memory. And it's related to a shift in a vacuum shift after the color wave passes. Okay, now what you might be asking is, how on the earth am I going to measure this in QCD, because color is confined in QCD? Here's the reason. Now, the people at LIGO are very optimistic in the coming decade they're going to measure gravitational. Now, these are amazing guys, amazing physicists. They're not going to live forever. They can't measure stuff at zero momentum. So how is it possible that they're hoping to measure this? And in fact, what happens at LIGO is you have a signal, you have a displacement, which is the memory effect, and then the memory gets pushed back by the pendulum, which restores the LIGO mirror. So you don't need an infinite, even though it's a zero momentum effect. This confuses me every time I say it, but it's true. Every time, you don't need an infinite amount of time to measure an effect at zero momentum if it's a pole. The Fourier transform of a pole at zero momentum is a step function. So the memory effect happens in a small amount of time and can be measured, and they're planning to measure it, and they probably will measure it. The same thing is true in QCD. You just have to measure the memory effect before confinement sets in. Now, there's something called the theory of color glass condensate, which was developed by McLaren and Venugopalan in 1993. I think the combined papers have 5,000 citations. It's a big thing in heavy ion collisions. And it's what is used to measure deep inelastic scattering near the Regge limit, where there's small momentum transfer. It's not what David is famous for. A different kinematic regime. It's a process which takes place on a scale large compared to the QCD scale. And for some reason, for which I refer my esteemed colleagues, this picture is supposed to be valid at scales large compared to the QCD scale at this color glass condensate. And so here's the picture of the deep inelastic scattering. There's a virtual photon that comes out. The photon hits, say you have an electron, and here we have a heavy ion, and these blue lines are the hard valence quarks. And the photon enters here. When it enters the color glass condensate, which really means classical QCD. So the color glass condensate, and this is apparently, arguably, it's arguably described by QCD, classical QCD with classical Yang-Mills field, altered only by the fact that the coupling constant runs. And you have valence quarks coming in here. In here you have classical QCD. The photon turns into what's called a quark dipole. It traverses the color glass condensate. It undergoes the color memory effect, and the amplitude or the cross section for it to emerge is the probability that it survives in a singlet. And so it's related, it's computed by the color memory effect. This is something that had been done decades ago. They just didn't call it the color memory effect. And they've been arguing about whether this has been measured or not. Venugopalan, some people think it has, others think it has. This is my last transparency. Okay, some people think it has, some people think it hasn't. What they all agree on is that the only way to solve the problem and be sure is to build the $100 million future electron ion collider, which they are actually very confident is going to get built, either at Brookhaven or at Jefferson Laboratory. It's going to get built, and it's going to settle this question of whether or not color memory is a real phenomenon. And open questions. All right, maybe I'll skip them. I think that all of this could be related. This stuff near the Reggie limit, a lot of the other stuff that is been talked about in our field, which also we're talking about small momentum transfers from highly energetic particles. And so the conclusion is that we spend a lot of time talking about the UV, but there's a lot that we don't understand about the IR, especially in Minkowski space. And the things that we don't understand are relevant not only to ongoing experiments, but to fundamental issues in holography, black hole physics, and quantum gravity. Let me stop there.
Thank you very much, but unfortunately, time is completely running out. So actually, there is no time for questions, but maybe we can accept one small question and then continue discussion later after the session. Okay, so do you have any very urgent question? No? Okay, then we can continue discussion after the session. Okay, thank you very much. Thank you. Now we have to go to the next talk. Next speaker is Shota Komatsu. Okay, his title is Non-Planar Correlators in N=4 Super Young-Mills from Integrability. So please start.
Okay. First, I would like to thank the organizers for putting together this wonderful conference. So today I would like to talk about my recent works on non-planar correlation functions in N=4 Super Young-Mills theory and their relation to integrability. So let me begin my talk with this, one of the most famous equalities in our field, ADS equals CFT. As we all agree, it has been providing a lot of deep insights into quantum gravity and interacting quantum field theory. But I think it is fair to say there are still many things to be understood. And one of the key missing links is perhaps the definition of quantum gravity or string theory in ADS spacetime. And I would like to point out that even the perturbative calc-level definition is missing in most cases because of the difficulties associated with Ramon-Ramon flux. And related to this point, there have been almost no checks for 1/n corrections, which corresponds to loops in ADS. And given such a situation, it would be probably a good idea to learn from some solvable examples. And the solvable example that I'm going to talk about today is N=4 Super Young-Mills theory in 4 dimensions. It is believed that this theory is solvable in the large n limit using integrability. And in particular, for the 2-point functions of single trace operators, it has been shown that there exists a map between single trace operators and the spin chains, and the spin chain turned out to be integrable. And on the other hand, on the string theory side, it has been shown that the sigma model in ADS is integrable. And using this integrability, you can compute the spectrum on a cylinder, which corresponds to computing 2-point function on the gate theory side using what's called thermodynamic Bethe-ansatz. And combining these two ideas, by now we have a very sophisticated method called quantum spectral curve, which allows you to compute the spectrum very efficiently. But this is not what my talk is about. My talk is about computing the non-planar higher point functions. But before doing that, I should perhaps review a little bit about planar higher point functions. So for simplicity, today I will focus on the correlation functions of half BPS operators, which are of this form. Here, phi is a scalar contained in N=4 Super Young-Mills theory, and yi's are null vector, null 6-component vector satisfying this relation. But I should emphasize that many things can actually be generalized to non-BPS operators. So let me start from the simplest higher point planar higher point functions, which is actually the 3-point function. At tree level, the computation of the 3-point function is rather easy because all you need to do is just do the planar weak contraction. And one important feature of this planar weak contraction is that the number of propagators between a pair of operators is completely determined by the length of the operators. For example, the number of propagators between O1 and O3 is given by this formula, which is L3 plus L1 minus L2 over 2. On the string theory side, the 3-point function corresponds to a spherical worldsheet with 3 vertex operator insertions, or equivalently, you can depict it as a pair of bands characterized by these 3 lengths, L3-1, L1-2, and L2-3. And as I said, the computation at tree level is rather easy, but if you want to do the computation at finite coupling, you need to resort to the integrability. However, in order to use the integrability, you need to consider integrable models on a pair of bands characterized by these lengths. However, but the problem is that this problem was never studied before in the literature. So we need to come up with a nice way to do this computation. So the key idea which allowed us to do the computation is to decompose the 3-point function into more fundamental objects called hexagons. More precisely, what we do is to take this pair of bands and cut it along those dashed lines and decompose into 2 hexagonal patches. And I should point out, this is essentially the same as the triangulation of the Riemann surface or the 3-puncture sphere. In practice, what I mean by decomposing the pair of bands into 2 hexagons is to take a partition function on a pair of bands and express it by inserting a complete basis of states on those dashed edges. And this procedure gives you an infinite series of expression of the 3-point function, whose leading term is given by the vacuum contribution. And the next leading term is given by the first excited state, which contains 1 particle on this dashed edge. And in the integrability literature, this particle is often called magnons because it is an excitation on the spin chain. And importantly, this magnon comes with some propagation factor, and the propagation factor knows about the lengths which characterize this pair of bands. As you can see, this is a little bit similar to gluing or sewing construction of 2D CFT, but the difference is that now I'm cutting the worldsheet in a slightly different way because essentially what I'm doing corresponds to the triangulation of the Riemann surface. And after doing the composition, the computation of the 3-point function boils down to the computation of these hexagons. So the next question is how to compute these hexagons. It turns out you can actually use the symmetry, which is the centrally extended PSU2/2, and integrability to compute these contributions from hexagons. For instance, one constraint coming from integrability is a so-called form factor bootstrap equation, which states that if you have a 2-particle hexagon with momentum P1 and P2 and swap the order of the particle, then you need to multiply the S matrix, which is determined by Nicholas Speiser. And by solving this kind of equation, you can get a very explicit expression for the 2-particle contribution. And this is the simplest 2-particle contribution, which takes up this form. Well, this might look a little bit complicated, but what's important is that you can actually compute it. And also, this encodes, this depends non-trivially on the Tofuft coupling. And you can also do the same for the higher particle contribution, and then you discover some factorization structure resembling Yang-Baxter. And by doing this, by using this hexagon contribution, by using this expression for the hexagon contribution, you can reproduce the perturbative answer up to 4 loops, and also the part of the result that's strong coupling. And so far, I've been talking about the 3-point functions, but all these can actually be generalized to higher point functions. To see how it goes, it is useful to go back to the tree-level analysis. If you consider the planar 4-point function at tree level, all you have to do is to list up all possible planar graphs and then compute the contribution from each graph. And as you can see, essentially the graphs are characterized by the number of propagators between operators. So what you need to do is to sum up all possible Lij's. And if you look at this picture, already you can see that there exists 4 hexagonal regions, one here, one here, one here, and one outside. So it is very tempting to replace this tree-level picture with this non-perturbative picture, in which you replace the propagators by these dashed edges, and then insert a complete basis on those dashed edges. So this is essentially our proposal for the 4-point functions. But I should emphasize that there is 2 important differences as compared to the 3-point function. One difference is that in the case of 3-point function, all these Lij's are completely determined by the lengths of the operators. But on the other hand, in the 4-point function, these Lij's are not determined uniquely, so you need to sum over all possible Lij's. And this is a bit analogous to the moduli space integral of the 2D CFD description of the string scattering amplitudes. And this point of view becomes important later in my talk. Okay, and another important difference as compared to the 2 and 3-point function is that unlike 2 and 3-point functions, which are essentially captured by scalar quantities, which are basically anomalous dimensions or a structure constant, the 4-point function is a non-trivial function of the conformal cross ratio. For example, by using the conformal transformation, you can place the operator 1 at the origin, operator 3 at position 1, and the operator 4 at position infinity. Then the position of the operator 2 is given by the conformal cross ratio z and z bar. And after going to this configuration, you can look at this hexagon and this hexagon. And then you find that this hexagon, this left hexagon, is in a sense canonical because it has a vertex at 0, 1, and infinity. On the other hand, this right hexagon is in a sense rotated or shifted because it has vertices at 0, infinity, and z bar. This means that this right hexagon is rotated as compared to the left hexagon. And in order to incorporate this rotation, you need to multiply this some weight factor, which depends on the cross ratio, when you sum over the states living here. I will not go into the detail of how to determine this WZZ bar, but the only thing I want to say is that this is basically purely kinematical, and you can determine it by using the symmetry argument. Now, including this weight factor, you can do the computation by summing up all possible states. Then the result reproduces nicely the perturbative computation. For example, 1-loop 4-point function and 1-loop 5-point function, and some higher loop result in some special cases. Now, okay, so far, now comes the main point of my talk. So far I've been talking about planar correlation functions. Then the natural next question is whether we can generalize this construction to non-planar surfaces. Well, it is actually not very hard to guess what we need to do for the non-planar surfaces, because what we have been doing is to take some Riemann surface, or take some pair of bands, or the 4-puncture sphere, and then decompose it into a bunch of hexagons and glue them back together by summing over all possible intermediate states. And it is essentially possible. Well, it is not so hard to do the same also for non-planar surfaces. So basically, what you need to do is to cut it into hexagon and multiply some weight factor and sum over all possible states, and also do some something like moduli space integrals. And let us be more specific. So to be more specific, let's consider the 4-point function on a torus. So if you identify this edge and this edge and this edge and this edge, this diagram describes the 4-point function on a torus. And this gives one way of decomposing this 4-point function on a torus into hexagon. Or this is a kind of triangulation of the 4-punctured torus. So again, our naive guess is to cut it into planar hexagons and insert complete bases along, on those dashed edges and sum over all possible graphs. Of course, this is easy to say, but in practice, it is a little bit hard because now you have a lot more hexagons. In particular, in this case, you have 8 hexagons, and there are many channels that you need to sum over. So in order to really do some reasonable computation, I need to go to some specific limit. And one simplifying limit is the limit where all the operators are very long. And when all the operators are very long, it turns out that the maximally connected graph will combinatorially dominant. And the reason for this is as follows. So if you consider, for example, length L operators, and then count the number of ways to split L propagator into n groups, then the combinatorial number is given by this expression, which is roughly L to n. So when L is very large, the configuration with larger n basically dominates. So in other words, if you have the operator, then operator of length L, then the operator wants to be connected to as many other operators as possible. This basically, if you do this for all the operators, then you typically get maximally connected graphs. However, there is also actually a competing effect, which comes from dynamical property of the hexagons. So if all Lij's are very large, the contribution from that kind of configuration are exponentially suppressed because of this e to minus energy times Lij factor. So when you consider large length limit, you need to combine these two effects. And if you combine these two effects, then you can conclude what dominates in the large L limit is submaximal graphs, which are obtained from the maximal graph by erasing a few connections. So this is an example of submaximal graph. And the solid line indicates that there are many propagators between the operator, whereas dashed line indicates that there are no propagators between the operators. So this graph can be obtained from the maximally connected one by erasing this connection. And going to this taking into account this submaximal graph, we can do the computation in the large L limit. And in particular, at the leading order in the 't Hooft coupling expansion and the subleading order in the 't Hooft coupling expansion, you can get some results which beautifully matches the direct perturbative computation. And furthermore, we can also make prediction for the next correction. So this, okay, by the way, let me emphasize this is a non-planar correction to the 4-point function, the first non-planar correction to the. Okay, so far so good. So I've been talking about the large length limit, but if you restrict yourself to just like one loop into 't Hooft coupling, then it is not so hard to also consider the finite length operators and try to compute the correlation functions of finite length operators. But if you start doing that, you immediately encounter some puzzles. So the puzzle is as follows. So our basic strategy of doing the computation is to start from tree-level graphs, cut it into hexagons, and dress them with excitations or magnons. Then you can ask, when we consider tree-level graphs in the first step, should we include this kind of graph or not? So this solid line indicates that there are connections. But of course, if you just consider the tree level, the answer is no, because although I drew this diagram on a torus, you can also draw this diagram on a sphere. So this is a planar diagram. However, the problem is that we cannot simply discard or throw it away, this diagram, because after dressing this diagram with Magnon excitation, this might contain a genuinely non-planar contributions. Essentially, dressing this diagram with Magnons corresponds to adding some gluon propagators. And what I'm saying is that even if the tree-level graph is this, if you start adding gluon propagators, then it might become a non-planar diagram. So the question is how to really get the correct answer without discarding necessary contributions. And the resolution comes from the analogy between the sum over the graphs and the moduli space integral over the moduli space of the Riemann surface. So the idea is as follows. So that the graphs that are secretly planar that I wrote here is basically the analog of pinched torus because there are no connection on this around this handle. So you can actually pinch the torus and replace it with a 4-point function with 2 extra holes, which came from the pinched torus. And essentially, in the usual context of the the theory of the Riemann surface, they correspond to the boundaries of the torus moduli space. And then our prescription is as follows. So you first sum over all possible graphs, including the graphs that look like planar, and then subtract the contribution of this pinched torus, which is essentially given by the 4-puncture sphere with 2 extra holes. So this kind of procedure in the usual context of Riemann surface is called stratification. So that's why we are calling it stratification. And then if you really want to do the computation using this picture, then you also need to know what these holes are. But first thing I can say is that because this came from the pinched torus, there are basically no dynamics at the holes. And another thing you can see is that if you start from drawing the planar diagram on a torus and then go to this pinched limit, then you can immediately see that these holes are nothing but the faces of the original double line notation of the Feynman diagram. And this kind of holes or face of the double line Feynman diagram also appears when you add extra probe D3 branes. And using this relation, you can actually compute the contribution from 4-puncture sphere with 2 extra holes by first considering the 4-punctured sphere without any extra holes, and then considering the second-order derivatives with respect to NC. Now, if you use this prescription, then at tree level, you just get 0 as we wanted. So you get something here, and you get the same thing here, and it gives you 0. But the important point is that if you go to order lambda, the one loop interfoot coupling, this cancellation is not exact, and you get something, and that something is precisely something that you need to reproduce a perturbative answer. So to summarize, this prescription beautifully works, and then we can get the correct answer. Okay, so let me summarize. So the main message of my talk today is that one can actually use the integrability not just to planar quantity, but also to non-planar quantities. And the basic idea is to sum over graphs and cut them into planar hexagons and compute the contribution from each hexagon, which are determined by the integrability. And I also said that in order to consider the finite length operator, you also need to do something called stratification. And about outlooks, the first thing I want to say is that it would be much nicer if we can better understand the relation between the graphs and the moduli space, and also the stratification. I think it is perhaps worthwhile to revisit the stuff discussed by Gopal and Razamat and Gopal and Pius, which are basically the free holographic dual of the free field theory. And it will be also interesting to try to resum or borrow resum 1 over n series in some special kinematics. In the flat space case, it was done by Gross-Menden and Mendel-Oguri. And it would be very nice if you can do the same also for this string theory. And finally, although I explained that you can do the computation using integrability, in practice, this way of computation is sometimes very complicated. So it would be much nicer if we can find ways to efficiently resum the contribution from Magnon excitations. Maybe we can, it would be very nice if we can find some method which also incorporates the quantum spectral curve. Thank you very much.
Thank you very much. So we have some time for discussions. So please. Yeah.
Thank you for the very nice talk. If you could go back at the finite L slide, because you consider there basically a planar graph embedded on the torus, but you could even consider in principle a disconnected 4-point function.
Yes. Yes.
And if you go to high enough order in virtual corrections or loops and so on, presumably that should also contribute.
Yeah.
And it seems to me that there is a risk that in the formalism of mirror magnons, you would have to compute an infinite number of mirror magnon corrections at a finite loop order.
Okay, so yeah, in order to really answer the question, I need to explain the technical detail. But let me just say that also in those cases, we actually need to consider this kind of stratification. And that basically a little bit fixes the problem.
So it's possible to put under control these infinite sets of mirror magnons?
Well, it's sometimes hard to do the explicit computation, but we can argue that, we can come up with a way to do the computation. Okay, yeah, probably it's better to discuss later.
Thank you.
Okay, so essentially time is running out, but maybe we can have 1 or 2 more urgent questions if you have. A question? Oh, yeah. Okay. So if not, let's thank the speaker again. And finally, let's thank all the speakers today for the very stimulating talks. Okay, so this is the end of the first session.
So attention please, this room will be closed very soon. So please go to the bus, please. Bus for Onnason area is already there. So please get in those buses, please.